So how you doing today?
Doing all right. How about you?
Not too bad. Yeah. Um, I know you've had some cool recent developments. I mean, obviously there's like James Webb Telescope, and then there's a lot of future projects coming out. Anything to update on that?
Well, yeah, there's always a lot to update. It's a good time to be in astronomy. So I think James Webb has definitely been a big deal, JWST. So, it's been sort of 30 years since we launched a big telescope like this that sort of looks in the optical, infrared, UV. So that's the part of the spectrum where we can see star-forming galaxies, especially. And so the previous one was Hubble. It looks in a little bit different wavelength range. So JWST really can see further back, and that's been really opening our eyes. And we're excited for a lot of stuff that's forthcoming. Here at UT, we're part of one of the biggest ground-based telescopes that's being built, the Giant Magellan Telescope. It's supposed to be completed sort of by the end of the decade in Chile, and each of its mirrors has 7 mirrors, and each of them is bigger than JWST's mirror, which is pretty wild. So that's going to be super cool. We've got something launching next year called the Nancy Grace Roman Space Telescope, and it's basically like the Hubble Space Telescope, same resolution, but a 200 times wider field of view. So whatever you could see in 200 snapshots with Hubble, you can see one shot with the Roman Space Telescope, which is pretty awesome. And I think a lot of people don't know that if you just look at one of those Hubble images, it's really looking at a tiny, tiny portion of the sky, like a tenth the size of the moon or something like that. So this is actually going to be sort of bigger than the full moon, the size of the telescope that you can actually see. So that's going to be amazing. It's actually a declassified spy telescope. So they got a call, NASA, about 10 years ago that was like, hey, we have something that's like Hubble, but 200 times wider field of view. Would you like it? Like, yeah, that'd be cool. But like, where did this come from? Oh, yeah, we've got 16 of these pointed down at Earth, and we don't need this one. So anyway, yeah, our technology is good, but not as good as some
Yeah.
3-letter agencies. So that's going to be really exciting. And then also on the ground, the Vera Rubin Observatory is starting observations in Chile, and they're going to basically take pictures of the entire sky that they can cover, which is much of the sky, almost covering that once a week for years and years and years. And that's going to be finding not just things that we can see in the sort of static universe, but things that are changing, right? So most of the time, astronomers are thinking, okay, the universe is pretty old. Things take a really long time for stuff to change. But there are things like at the end of a star's lifetime, it'll blow up, right? And that takes almost no time whatsoever. So you'll see something shoot up in the sky, and you've got to be ready for it. And this thing will be able to tell us, hey, let's point our telescope at that. So I think we're set for a whole bunch of new discoveries with all these kind of new facilities coming online. It's going to be super awesome.
I saw like a kind of a clickbaity title that was talking about how we'll be able to see a star explode pretty soon.
I think that's definitely a dream, that is a possibility, right? I mean, so the key is stars live typically for the shortest lived stars are 10 million years. The longest lived stars actually live longer than the current age of the universe. So anything that's less massive than about 70% of the mass of the sun, even if it was born right after the Big Bang, it's still surviving today. But those massive ones, they live shorter lifespans, so tens of millions of years, 10 million years. So you might think, okay, that's pretty long compared to human lifespan still, but there are a lot of them out there. And so the key is, can we find this signature that it's about to die? And then can we get there fast enough to see it? And I think we're at the edge of that. And I think these kind of new facilities will allow us to kind of do that, hopefully, which would be pretty awesome.
Bit of a layman question, but I was curious because I've had people tell me this my whole life that when you look up at a star in the night sky and it's twinkling, that means it's dying.
No, that's more what's happening with the light as it's coming through the atmosphere. So no, those twinkles are no need to worry. Star's fine here.
Yeah, because I was looking up and I was like, every star is twinkling.
Yeah,
That doesn't make any sense.
The end is near.
Yeah.
You're all good.
Okay, and then I want to jump back to try to put into perspective how small the portions of the sky that you guys were looking at compared to the moon. I watched one of your talks from a while ago, and you had like a really nice figure that had the full moon, and it was like this tiny little box. How do you pick and choose like which tiny spot in the night sky do I want to look at?
Yeah, that's a great question. So there are a lot of considerations. Some of them are what's been looked at before, because sometimes then you can compare to other observations. You can get observations from other wavelengths that complement what you're looking at. Sometimes you want to make sure you're looking at something that is kind of continuously viewable. This, just based on where the satellite is, sometimes it just can't look at certain areas of the sky. Other things you want to do are like, you don't want to look at the sun. Like looking at that, I mean, some telescopes do that, but like JWST, you don't want to be pointing at the sun. So you want to be pointed away from that. You want to be pointed away from other kind of bright things. So there are a lot of sort of initial considerations there, and based on those, people have chosen certain areas that are good to look for, like really dark parts of the sky that look like they're empty, and then when you look deeper, there's just tons of stuff there. So that's like one way you can do it. But a lot of times, we want to not just know what's in that part of the sky. We want to kind of know everywhere, and so people take lots of different areas that they're looking at just to make sure we didn't get lucky or unlucky with where we looked.
Yeah. So if you're looking at something that's really far away or really old and really faint, then you want to limit the amount of like bright stuff that's kind of in between you.
That's exactly right, because the amount of light we get from any object falls off like the distance that object's squared, so it really falls off fast if things are far away, and so we want to make sure that we're really only getting stuff from that sort of portion of the sky.
Yeah, thinking about it, and that and the inverse square law, that light has to be so faint.
Yes. It's pretty incredible what we can detect. Yeah.
Do you know how much more powerful those telescopes are than, like, say, the human eye?
Oh, that's a great question. I don't off the top of my head know a great comparison, but like way, way more powerful, right? Yeah.
And then with the Magellan telescope, comparing that to the James Webb telescope, I mean, you're saying it's so much bigger. What about the atmosphere? What is the atmosphere doing, and how is that going to affect the telescope?
Sure. So, it's easier to build things on the ground. You don't have to launch them into space, so you can make them bigger. Right? Everything that you launch into space, it's expensive and challenging to launch big things. But when you launch something into space, you are beyond the Earth's atmosphere, like you're saying. And the atmosphere, kind of the issue with the atmosphere is there's water vapor in there, and that can cause change in the light that you're getting. And there's also turbulence in the atmosphere, so that changes kind of how the light waves look when they're coming towards us. So one thing that the Giant Magellan Telescope is doing, and that will do, and that other telescopes have started to do in the past, say, 20, 30 years, is they actually have what are called adaptive optics. So the mirrors actually deform to look like those deformations in the atmosphere. So they actually shoot a laser out. They see how the laser changes in some sense, and then they change the telescope to counteract those changes. So there are ways you can adjust for the atmosphere. That's called adaptive optics. And again, this is originally a military application that came to astronomy. And so that's going to be one really, really cool way to do things. So another advantage, it'll be able to collect a lot more of this light because it's so much bigger. It'll also have a bigger kind of field of view again, so it'll look at a little more area of the sky than James Webb is doing. And so that'll be really handy. And then I think the other thing is, since you don't have to launch it 1.5 million miles away, then you're actually able to make changes to it and change the instruments. So we sort of know what the first set of instruments on it will look like, and those will be specialized ones to say look for life on other planets, signatures of life on other planets, to be optimized to look for distant stars and galaxies. But if they find something cool, they can change out what's on there and like get something that's even more specialized, or it looks for something else. So it's easier to change things on the ground. And so we're hoping that GMT would, operate for a very long time and would be able to be continuously updated as it operates. So those are some of the differences.
Yeah, that was a really cool thing that I figured out when I was like researching telescopes and everything, is that these big observatories, like they start out as one thing, but then as technology gets better, you start replacing parts and you start doing all these things. So it's not really like a supercomputer where the lifespan is, let's say, a couple of years. Like you're looking at decade scale.
No, that's right. Here at UT, we operate the McDonald Observatory, and that just celebrated its 85th anniversary, right? And some of the same telescopes are still there. It's just there's different, machinery behind it and different behind the scenes stuff. So things look very different than they did 85 years ago, but you can still be at the forefront. And since UT, owns and operates it, that means that we can say, hey, let's adapt it this way to fit some new problem. And I think one great example of that is those extrasolar planets. It's really been a leader in helping to characterize them because we have scientists here who've worked on that, and they can work with the instrument builders, the engineers, and say this is really what we need. And then we can go out and do it on the telescope. By we, I mean somebody else. I don't observe extrasolar planets at all. So,
and then the Magellan Telescope is, correct me if I'm wrong, I want to say it's unique because it has this approach of having all these tiny little mirrors, not tiny, huge mirrors, right? But relative to the entire thing, like small mirrors that are going to make up the overall, I guess, lens. And James Webb is different, right? James Webb is...
That's right. Yeah. So James Webb has one primary mirror, so just one big old mirror. And that is, I think, a 6.5 meter in diameter mirror. Each of the 7 mirrors that Giant Magellan has are 8+ meters. Okay, so you've got a total size of sort of 30 meters on a side, but like it's just a bunch of 8-meter telescope. I mean, 8 meters is pretty big, right?
That's huge.
That's huge, and that's one of the 7 mirrors. So I've seen how it's laying out. The whole thing is going to be 30 meters, right? So like 30, from the end zone to the 30-yard line. That's a pretty big mirror. And that's what there's 3 planned telescopes kind of this scale, the Giant Magellan Telescope that UT and a bunch of other universities are doing in the U.S. and with foreign partners. There's also a 30-meter telescope that's planned by another group of U.S. astronomers with a couple of foreign partners. And then there's the European Extremely Large Telescope. We're sort of bad at naming things in astronomy. And so that one actually has even more smaller mirrors that are sort of going to be tiled together. So all of the ones that are that big need to be planned like that, because there's no way to make a 30-meter mirror that's sort of like one piece. It'd just be, I think, too fragile and too difficult to do.
Yeah, and I'd imagine the lifespan on that would be pretty sketchy.
Yeah, and it's also so heavy if you make one big mirror like that, right? That it's just completely unwieldy. You can imagine how hard it is to make even one of these, right? One of these 8-meter mirrors. The process is incredible. They build them under the football stadium at the University of Arizona.
Wow, that's cool.
There's like this huge lab, and it takes months to cool one, months to polish it. It's like any one of these is just an enormous investment. Yeah, not just like you break one of those, you're in big trouble. Yeah.
Do they use like a special type of glass for that? That's not really.
Oh yeah, no, you definitely need to have one that has certain purities, and you want to make sure that it has known temperature characteristics and all that, and they control the process very well the whole way through.
Yeah. That's really interesting. And I know that the observatory in Chile is being built somewhere around 8,500 feet at elevation. And so for somebody thinking like, okay, well, if you want to see a lot of the night sky, why don't you just go to like the highest mountain that you can find? Why like 8,500 feet?
Well, yeah, there are a lot of considerations that go into it. You might also say, why are you doing it in Chile when you could just build it anywhere closer in U.S. But again, the atmosphere really gets you. So you want something with very little water vapor. So you need a desert, and you need something where the way the light is dispersed it doesn't get dispersed very much. And it turns out there are a few sites in the U.S. that are okay for this. But the very best ones are sort of mountains in either Chile or the South Pole, or Hawaii is another spot, in the U.S., but it's, again, kind of isolated. And, you want to go high, but you don't want to go too high. It's challenging to bring things up once you get to the top of the highest mountain. And also then the atmospheric conditions can be different, like the pressures and the temperatures are different up there. You get a lot of wind and other things at the top of the highest mountains that you don't want to have to deal with. So you're sort of balancing out, okay, how much atmosphere do we have to deal with versus how easy is it to get the stuff there and have people live there to operate it and all of that.
Yeah. Do you know how much of a Chilean project it is versus a U.S. project?
Well, I think that clearly it's very important to have the infrastructure and all of that there, and so that's sort of being built locally. I think it's funded a lot by the consortium, but there's a big partnership with the government, and then they'll get a lot of people there are working on it, and so they'll have time on the telescope. So I think it's sort of putting in local resources with a lot of these external ones. So it's mostly external resources, but obviously you can't do it without the help of people on the ground there, and without the permission of the government and all of those kind of things. So it's these big things are like international treaty level discussions, right? So I stay away from that.
A little bit above the pay grade.
That's right.
Yeah. I guess just one more question on that topic. I think it completely evaded me. Yeah. No, yeah, you're all good. Man. Yeah, okay, so usually that happens to where like I have the question in my mind and then I forget to write it down, and then I'm like, "Oh, this is going to be awesome. Like I have this question ready." And then I like reply to you, and then it just completely leaves the RAM. Like
yeah. Maybe it'll come back.
Yeah, it'll come back. What about dark matter? Let's I really wanted to say let's shed some light.
There you go.
On dark matter.
Definitely.
What is it exactly?
Yeah, I think one way to think about dark matter is something that is our lack of understanding about what's going on in the cosmos. So really, I think the statement would be that if you take Newton's laws that we know apply really well, or if you want Einstein's laws, if you really want to be accurate about the gravity, but Newton's laws work pretty well for all of this, and you apply them to the light and mass that we can see in the universe, then you actually don't get answers that agree at all with observation. So what you find is that there's a lot less matter that's gravitating there than you need to explain how fast things are going, for example. So the easiest way to think about it is, the way Kepler or Newton or whoever would think about the orbits of the planets is how massive the sun is, and then that can give you laws about how fast the Earth goes around the sun. We do the same kind of thing for stars and galaxies, and so you can measure how much mass there is by sort of how fast stars are going at a given distance, for example. And if you do that, and you just take the mass that you see they're whizzing around way too fast to be explained by the amount of mass that you can actually see. So either that means that we just happen to see it at this place where every star is about to be thrown out of every galaxy. That would be a little weird. Or there's some unseen mass there that you need to explain that extra bit of gravity, or Newton's laws are wrong. Those are the sort of three possibilities. And we know it's not that it's not regular atomic matter that could be there. So that might be the other thing you might think. You might just think, okay, well, there's stuff we don't see, but why do you have to invent something that is not the regular atomic matter that we're used to, that makes up the table, you, me, everything we know? But we can sort of measure very well how much of that atomic matter there is in the universe, and that doesn't really add up. And so the interesting thing is you can look on galaxies and say we need this dark matter, right, to explain how fast things are going. You can look at the whole universe and say how much mass is there, and that doesn't really add up. But then everything really starts to fit together if you just say there's this matter that doesn't really interact with light, but that does have gravity. So it's really just matter that has gravity but doesn't interact with normal atomic matter that we're used to.
Mm-hmm. Does it interact with anything else besides gravity?
So as far as we know, gravity is the only thing it interacts with. It's possible that it has some very weak interaction with the weak interaction. So there are four forces of nature: the electromagnetic force, which is one of the ones we're most familiar with, that, and gravity is another one. But then there are two nuclear forces, the strong and weak nuclear force. So the strong nuclear force is what kind of binds things into nuclei, and the weak nuclear force governs the decay of those nuclei. And so it may interact with the weak nuclear force. That's the sort of most standard picture of dark matter that people have, but we haven't ever seen that, so we don't really know.
And do you think it's like a particle, or maybe some kind of foreign concept that we're not super familiar with? Like what's the leading theory on what dark matter might be?
Yeah, that's an excellent question. I think that if you asked 30, 20, maybe even 10 years ago, pretty much everybody would have said, oh, yeah, we think it's definitely a particle. We even have some pretty good ideas about what that particle could be, what its properties would look like. It might be something that's maybe 200 times the mass of the proton, kind of like that. There's a lot of good reasons for that. But experiments have gotten so good at looking for those kind of particles that we can now really say, all right, that's still a possibility, but it's not at all like the slam dunk we were thinking it was a while back. So I think people would still pretty much bet money on it being a particle, but the properties of that particle could be really different. So, some people are thinking now that it could be not more massive than the proton. They're thinking it could be the lightest particle we know of out there. So way, way, way less massive. So low mass, there have to be so many of them that they kind of behave like a wave more than like a particle or like a field. So that would be an interesting possibility. Another possibility that seems unlikely to be all of dark matter, but that could contribute, is primordial black holes. So things that are black holes that are left over from the Big Bang, that would act like dark matter. So there are a lot of sort of more exotic possibilities that people hadn't really thought as much about, that people are studying in more detail now. But I think still most people would bet on it being a particle, I would say.
Primordial black holes, do you mean like these supermassive black hole structures that are kind of keeping, our galaxies and stuff together, or smaller black holes within the galaxy that's adding mass that we're not directly observing?
Yeah, excellent question. So I think that these would be black holes that wouldn't have come from the death of a star or the collapse of a big gas cloud, maybe hundreds of millions of years after the universe started. This would be something that happened in the first few instants of the universe. So in the first few seconds, maybe something like that. And then it could have grown and gotten bigger by accreting matter like black holes normally do, and maybe sits at the center of galaxies. And this goes back to your question about James Webb Space Telescope, that one of the big surprises there is that there are more black holes than we thought in the early universe, and they're more massive than we thought. So this gives maybe a way that they could have gotten so massive. Otherwise, it's very confusing to see how we got so many black holes and how they got so big if they really started out from stars or gas clouds that they just didn't have that much time to grow.
Yeah, now you're getting into the idea of like what came first. I know that's a question that's posed in your field. Like, do we have black holes that are kind of seeding the beginnings of galaxies, or do galaxies over time start to form by themselves and then a black hole kind of finds its way into?
Definitely, you've done your homework, I can tell for sure. So that's a big question, and it's been a big question for a while. I was on a panel every 10 years. The whole astronomy community sort of comes together and asks, okay, what are the big questions in each subfield of astronomy? So I was on the Galaxies panel, and we came up with the questions, and we look back at the previous 10 years, and they had some of the same questions, and even 10 years before that, similar questions. And the question of how do black holes and galaxies grow together, right? And which comes first? What's the chicken? What's the egg? That's definitely a big question. And I think that we're starting to maybe push back the veil a little bit and see some of those answers with JWST, but we're not quite there yet. I think understanding which came first. And so one of the things we can try to do with JWST is ask, do we see black holes that are relatively more massive in the early universe compared to the galaxy, or are they relatively less massive compared to the galaxy? Because that might tell us, okay, the black hole came first if it's more massive compared to the galaxy than what we see today. And that sort of looks like what's happening there. But we don't really know for sure.
How do you tell the age of a black hole?
So you wouldn't really tell the age of the black hole, but you would tell, you have the galaxy, its mass, you can measure its mass, hopefully, and you can measure the mass of the black hole. And so you can at least see, all right, for that one galaxy and its black hole, is that black hole sort of, instead of being 1/1000th the mass of the galaxy, is it 1/100th the mass of the galaxy? And then okay, that galaxy is way bigger than the typical black hole is in a galaxy today.
Oh, so it's more like the mass distribution.
That's right, okay. Exactly. Comparing the mass of the black hole to the mass of the galaxy.
What about uncertainty in calculating the mass of the galaxy itself? I know that, like, calculating just a single star can leave you with a lot of uncertainty.
Yeah. So, theorists, we get to do things pretty easily, right? Like, we just get to make up the numbers and say this is what it should be. Not exactly, but there's some of that where if we're doing simulated data, we know exactly what the mass of things are. I can say I'm putting a star here, it has this mass, and I know how it'll evolve forever. In the universe, we actually don't really measure mass of the stars. We measure the light, and then we try to infer the mass from that. And so we need to understand the distribution, how the light compares to the mass, so how much light you get from a given mass. And so there is uncertainty there, because then you need to know how the masses of stars are distributed. And that's a big question in my field and in the field of star formation also, is how many very massive stars are there versus how many low mass stars. And that does give a big uncertainty. And that actually relates to the JWST observations also. Some of the first observations that came out, people said, oh my gosh, these things are so big and so massive that they got to be too massive compared to what we could get in the universe that we know. And one of the ways out of that is to say, no, they're very bright, but the stars that formed back then were maybe more massive than the stars that form today, typically. And so they're emitting a lot more light. The total mass isn't sort of out of the budget that we could allot for mass in the early universe. So that's still kind of under debate a little bit as to why they're so bright. Is it changing the amount of mass? Is it because of the black holes? Is it something else? But those are the questions that we're still talking about a lot in the field.
Yeah, before we go too much into galaxy formation, I want to go back to dark matter for a second. So I know that there's some theories that so on the side of like it being maybe a particle, there's neutrinos and then axions is kind of like the leading two theories of what it could be. I was wondering if you could talk about that a little bit.
Sure. Okay, so neutrinos, we know there are neutrinos. Okay, so there are 3 neutrinos in our standard model of particle physics, and the standard model of particle physics is the best tested sort of theoretical model we have out there. And we're still trying to measure the masses of those neutrinos. We know those can't be the dark matter, though. Okay, they would behave very differently than the dark matter that we're looking at. They would have to be much heavier than we know they are. We have limits on how massive they are. The fact that we can actually even put constraints on the mass is pretty cool. And actually, from cosmology, we're starting to measure the masses as well, and so that's pretty fun, different way to get masses. But those wouldn't be the dark matter particles. But there could be companions to these standard model neutrinos that we'd call sterile neutrinos, so they wouldn't interact in the same way. But the models that say, why are neutrinos so low mass, and why do they have such little interaction? Well, that could be because there are other neutrinos that we don't really see now, and those could be dark matter. So that would be one possibility. And they'd be much more massive than the neutrinos we know. The neutrinos that we know are pretty low mass. They're much less massive than any other particle we know that has mass, typically. So that's one particle. An axion is a particle that we have never detected, but most people think the axion exists. It's because it helps explain certain problems in physics and particle physics. So it explains measurement of the magnetic dipole moment of the neutron, which is not super important, but it explains why some number is what it is. Okay, and if you say we have this particle, this axion, it can really make that very understandable. The problem is there's a lot of possible masses the axion could take on. But the normal axion is one of these particles that in our galaxy, it's so low mass that basically all the axions would almost be overlapping. They'd be more like a field than individual particles interacting one-on-one. So there still are particles, but they're sort of coherent. They act together as a field. And then there's also other particles that could come along with these that would be ultralight axions that would be incredibly low mass. So they'd be sort of not just less massive than an electron, they'd be 30 orders of magnitude less mass. Well, let's say 25 orders of magnitude less massive than an electron. So tiny, tiny masses. And the thing that's interesting about that, well, there are lots of interesting things, but the sort of size of a particle goes inversely with its mass. So the bigger the mass of the particle, the smaller the size. That's sort of why we don't see quantum mechanical effects, the effects of particles for like us, right? We're sort of, the size would be so small. But for these tiny, tiny low mass particles, the size is very big. And in fact, that means that they start to have effects on galaxy scales. And so that's why people are thinking about them as candidates for dark matter and looking at galaxies. And then the other particle that people talk about a lot is a weakly interacting massive particle. So they abbreviate that as WIMP. Okay, so you hear sometimes in the field people talking about WIMPs a lot. They're not sort of talking about the, people who haven't hit the gym a lot in the conference, which is most people probably. But these are actually particles. And these particles are the ones I was talking about. They're maybe like 200 times the mass of a proton. And again, sort of like the axion, if these WIMPs exist, then they help explain a lot of other things. And so that's why people were really excited about them for a long time, and still are. But the simplest version of these WIMPs doesn't seem to be what dark matter is. And so now we're looking harder. So those are some of the biggest candidates. So you've got them exactly right.
Gotcha. Okay. I didn't know that about neutrinos, that there was evidence that it can't be, or like not the neutrino, like the neutrinos that we observe. There might be a different neutrino.
Yeah. So people really, in like the early 1980s, people were really excited about neutrinos maybe being dark matter, but you could see that the distribution of galaxies would look very different if the neutrinos in the standard model were dark matter than it actually does. So that's one of the first places actually that people were able to make these connections between the physics of the very small of neutrinos and the very big, the distribution of galaxies over the whole universe. And that was done with computer simulations. So that's pretty cool.
Yeah, those computer simulations are amazing. I do want to ask a little bit more about those later.
Yeah, sure.
But also, what was really interesting to me is you explaining how axions almost behave more like a field. Mm-hmm. And would you say that they behave kind of like a quasi-particle, like a phonon or something, like the different, vibrational modes of atoms within a substance, or something more along the lines of that?
Yeah, I think you can see that. So there would be excitations in there. They sometimes would have sort of coherent effects that would form sort of dense structures in the center called solitons, and they're quantum mechanical, and so they can have turbulence in this field that acts based on the particle nature of this stuff. So if you simulate it, you can see very clearly that they have sort of these waves that can go through this field that wouldn't happen with particle, dark matter that doesn't have overlapping sort of sizes. So yeah, there's a lot of effects that are kind of neat like that would happen in this axion coherent field dark matter that wouldn't happen in sort of standard particle dark matter.
That's really, really cool.
Yeah, it's definitely pretty awesome.
Yeah. So when you say there's like a high density distribution, is that like there's a lot of particles in space that are in one location, or is it like the actual more like building blocks or like subatomic structure of the particles are in one place? Yeah,
great question. So basically the idea is we know approximately what the density of dark matter is around us. So to first order, it's like maybe a proton per cubic centimeter, let's say, worth of mass.
And that's like really small.
So a proton is pretty small mass, right? So in particle physics, this would measure it in its energy equivalent. So that's 1 billion electron volts. Okay, so that's one particle. Let's say there's roughly one of those in a cubic centimeter. So there's a billion electron volts worth of mass in a cubic centimeter. Okay, now if you make these things a lot lighter, you need a lot more of them, so that there's one of those if it's a proton, right? Now if you make it 1,000th the mass of a proton, you need 1,000 in a cubic centimeter. These particles that we're talking about are 10 to the minus 22 electron volts. So you need 10 to the 30 of them almost to make just one proton. So it'd be some enormous number in every little part of space, whereas you might just need one proton to do it. And so there's an enormous number of these things everywhere. So they really are just a ton of these things in every part of space, if that's the answer.
That's really, really cool.
It's pretty wild.
That's bizarre.
Yes, yeah. Very bizarre. I agree.
That would be crazy if we had eyes that could see that.
Oh, man. Yeah.
I don't think you'd be able to see anything. I mean, maybe density variations, but you'd be like swimming through this big soup.
Yeah, it'd be amazing.
Yeah.
But I'd probably want to turn that switch back off too at some point.
So when you refer to dark matter as having mass or having effects on gravity, it does remind me of some of Einstein's theories in like E equals mc squared, mm-hmm. and how mass is related to energy. With normal matter, that's the case. Is dark matter the same?
Yeah, dark matter would be the same. So the equivalence of matter and energy comes in a couple of different ways. So one is that sometimes matter can be converted into energy, and energy can be converted into matter. And so, for example, for these WIMP particles, that's how we think they'd be created. So it would actually be some bits of light or something like that would smash together, and there'd be enough energy that they'd create particles. So that would be sort of taking energy and turning it into mass. The other way that, and it can go the other way. So if this is true, actually in very dense parts of the universe, sometimes two dark matter particles would smash together and just turn into light. And so that's one way that people look for this. They actually look for light coming from places where there's a lot of dark matter, they think, but not much regular light. And so that's a way you can look for dark matter. The other manifestation of Einstein's models there is that, light reacts to both matter and energy, and so you can see how the path of light changes based on the amount of matter and energy there. And so dark matter again would behave just like regular matter and energy insofar as gravity in that way. Yeah.
What wavelength of light would be given off by the collision of two dark matter particles?
Yeah, excellent. So normally, it depends on sort of on the properties, the exact properties, but it would be pretty high energy stuff. So we're talking about gamma rays typically. So we're talking about things that are hundreds of billions of electron volts slamming together, and so it's producing light that has energy that's hundreds of billions of electron volts, and that's much more energetic than the light that we kind of are used to, or even than X-rays. So it'd be sort of the most energetic rays out there that you can kind of get are gamma rays. Now, it wouldn't be the most energetic of those. You can get things that are bigger than that. But yeah, effectively, it's just sort of two particles smashing together and producing two particles of light that have the same energy as those particles had in mass via that E equals mc squared equivalence.
And when you talk about dark matter and its kind of relation to energy, that does not entail dark energy. Dark energy is not the energy associated with dark matter.
That's right. So that's really important distinction. So, like I said before, astronomers are really bad at naming things, and particle physicists probably too in that sense. So dark matter and dark energy both have dark in them, but they're very different concepts. So dark matter is something that really behaves like matter and just clumps up with gravity. So it really does behave like regular particles. Dark energy is something that, as far as we can tell, doesn't have properties that differ anywhere in space or in time. So every part of the universe has the exact same amount of dark energy at all times, as far as we know, and it doesn't clump up. It doesn't diffuse out, right? If I have a box full of marbles and I stretch the box out because the universe is expanding, there are fewer marbles per unit volume of the box. If I do the same with dark energy, actually there's more dark energy in the box, so the density of dark energy stays the same. So as the universe expands, somehow more of this dark energy is being created in the expansion, such that the density of dark energy stays the same. So it's this very weird stuff.
When you talk about the expansion of the universe, I want to be right on the semantics here. Is it like the creation of new space-time at some kind of boundary that we're unaware of, or is it like the actual stretching of what we have already?
Yeah, people actually argue about this still in some sense. I wouldn't. I think it's really, things are expanding, but it's not like everything exactly is stretching. On the other hand, lots of things do stretch. So galaxies don't stretch. The things that are bound by gravity aren't being pulled apart that way. But the distance between 2 points is changing, right? And it does seem like there's more space being created. There's more volume of the universe. So something is stretching in that way. And as light traverses the universe, its wavelength gets stretched as the universe expands. So in that sense, we can kind of think of it as stretching. So a lot of times when we talk about the expanding universe, we use a stretching analogy, like either a rubber sheet that's sort of stretching or something like that. And that works pretty well for most things, but not perfectly for everything. It's pretty complicated. Some of it is pretty simple and some of it's pretty complicated, and people still, who are real experts, still argue what does it actually mean.
I really liked Neil deGrasse Tyson's question at that panel where he said, do you think we are even smart enough to ask the right questions?
Yeah.
And it was like a bit trippy to think about, because it's like some of these problems are way past our, human intuition, like with quantum mechanics, and then when you get to like, what does it actually mean for the universe to be expanding? It's strange.
Yeah, I think, that's always one of the things we're trying to do as scientists is not just do what we've done before, but figure out what are the right questions to ask. And I think that is one of the things that really separates, some of the great scientists from other people, is really knowing, okay, what is going to be interesting to ask. And it's also a place where sort of theory and experiment, or theory and observation, have a lot of interplay, because you might not know to ask a question until you've seen something weird in an observation or an experiment. Or conversely, you might say, well, I've got this great theory and it predicts this weird stuff, and then somebody can come out and go and measure, is that the right thing? And so they sort of push each other to understand the universe. But I think that's sort of a philosophical one, right? Like, are we ever able to, do we have the right language for this? Do we have the right ability to ask the right questions? I certainly don't, but somebody's got to be able to figure this out, man.
Yeah, I mean, you could turn the different knobs on simulations all day, but if you're not, almost, maybe tuning is the right word. If you're not like trying to tune the model or the simulation and the observation for the question that you're asking, then you might end up with data that completely misses the point of, whatever discovery you're trying to make.
Yeah, definitely. And I think the other aspect of that is, if you're so focused on trying to explain, something with the models that you have, you might miss the possibility that there's another model that could explain it and explain something else. So there's always this balance of like, are we testing our models and sort of refining them, making them slightly better here or there, or are we looking for something totally new? And, both kinds of science are really good and really important. And a lot of science now is sort of, okay, we think these models work really well, so let's figure out and apply them to this new regime. So we have a telescope that shows us a new part of the universe. Let's test the models that we had before. And if there's something new that comes in, does that mean you throw out that model? Probably not, unless you really say, okay, those new observations aren't just a little surprising in the context of the model, but they're really things we can't explain with the model that we have. And so it takes a lot. Usually, the more advanced and sort of tested a model is, the more evidence you'd want to throw it out and start new with a different one.
Yeah. Do you find a lot of physicists trying to cling on really tight to the theories that they have, and they are almost extra skeptical of things that come out that are trying to disprove or shake up the field a little bit?
Yeah, I think that I think I see both sides of that. I think you definitely see people who are maybe a little too reluctant to say, could there be something different, right? And we've got this model, it's fine. I'm sure there'll be a way to accommodate these new observations. And then I think there are people who are too willing to say, new observation, everything we know is wrong, let's start from scratch, right? And I think that the real, everybody's dream would be to find something that says everything we knew was wrong and we've got to come up with a new model and here's the new model. Like that's what everybody kind of wants at some level, right? Is to have some new insight and new understanding of the universe. But usually it's not the case. And what we need for coming up with new models is an alternative that explains everything the old one did and the new observations. And that's really hard. And that's why I think, a lot of times people say, I don't really like dark matter or dark energy. It doesn't give me the right vibes. It doesn't feel right. And I say, I think that's great. Let's come up with a theory that explains everything that dark matter can explain and something that can explain. And then I'm definitely all ears. Let's work on that. But so far, there hasn't been anything that looks like that. People have tried to modify gravity. Even, Einstein modified Newton's laws. You could try to modify Einstein's laws to explain away dark energy and dark matter. So far, there's been no compelling way to do that. And so that's why, even though it seems a little weird, people are still very much on the bandwagon of dark matter and dark energy are the best explanations we have for explaining the universe.
Yeah, that reminds me of that recent paper. I'm actually not sure how recent, but a relatively recent paper that was saying that there was evidence that the universe was like twice as old as we think it is. What evidence did they have for that?
So this comes back to the JWST observations. So one of the first sets of observations was very massive and mature-looking galaxies in the early universe. And we talked a little bit before about how the masses are a little bit uncertain, but I think there's definitely a lot of mass and a lot of light that was built up in a short amount of time. And so if you could say, well, no, the universe actually was there was much more time to get to that, then it would make it a little easier to explain with our current models of galaxy formation. But the trouble with that is then you have to throw out all the other data that says, well, everything matches up pretty well with the universe being around 13 billion years old and expanding like this since the beginning. And so that's another example where you want to change your models to fit one piece of data. That's a little dangerous because then you have to make sure it hasn't ruined the agreement you've gotten with all of the other data that's out there.
Yeah. And that also reminds me of the Hubble, basically the cosmological constant for the expansion of the universe was
Hubble tension.
Hubble tension, there we go. Tension was the word I was going to say, but I was feeling like doubtful of like if that was the right word.
Trust yourself.
Okay.
You got it. Yeah.
Hubble tension problem. So if I'm not mistaken, that's basically we can measure the age of the universe through just cosmic background radiation, and we can also measure the universe the age of the universe through the rate at which it's expanding. And those two compelling, like pretty solid methods give different answers on the scale of like 200 million years or so.
Even bigger than that, I'd say probably. Yeah, but that's the basic idea, right? We can measure the age of the universe by assuming a model and looking at the distribution of its earliest light, and that tells us sort of how fast the universe has been expanding, or another way to think about it is the age. And then the other way we can measure it is, just directly going out and seeing how fast are galaxies going away from us. And that gives us an expansion rate or an age. And the ages disagree by about 1 billion years.
Oh, wow. Okay.
And the expansion rate disagrees by about, maybe 8%. 8 or 10%. So that's, doesn't sound that big, but it's like pretty precise measurements nowadays. And so that's one of the biggest questions out there is there really this disagreement between these two pretty solid methods, like you're saying? And if so, does that mean we need something new in physics? And I think that's been something that people have been really excited about and thinking about a lot. And for me, it's exciting because again, there aren't that many ways you can change the cosmology models to fit our data, and so there's actually only a very small. It's not like some of these problems where, well, I could do anything anywhere and that'll work. There's really only a very small area where you can start to change things and not ruin the agreement with everything else. So they're very testable models, and that's a good thing. And I think we should know the answer pretty soon, within the next year or two, whether there's any way you can change our cosmology by just adding a little bit into it and explaining this difference that way. The other possibility would be that our measurements nearby, which are direct but require a couple of steps, that like one of those steps, there's a little something we don't understand. And there's some evidence that might be right because we have a few different ways to do it nearby and they come up with somewhat different numbers. But JWST is helping with that also. And then it's measuring some of the stars we use to get out to more distant galaxies. And so then we're going to try to figure out how well we can do that. And that's pretty exciting. So that's a big area where JWST is contributing as well to this Hubble tension.
Yeah, I thought it was absolutely fascinating how you guys are playing around with this idea of adding a new kind of cosmological force or cosmological entity. I don't know what the exact right word is, but something like dark matter in order to explain that age difference. Is that how I guess well received is that theory by the field? And
well, I think that opinions vary, as they say, but I think that a lot of people who work in particle theory are excited by it because it would require some new forces and something that they could study. And again, I think a lot of people have been interested in it because this disagreement has been so persistent that this is one of the few ways you could do it. And it wouldn't be, we need to scrap everything and start over again. It would basically be saying, look, we thought there were these components of the universe. There's actually one more component. And so when you add that component in, the assumptions we made have to change a little bit about how much of each of the other components there are, and then we can explain everything again. But that sort of changes our inferences about the age of the universe, about how much matter there is in every little bit of volume and things like that. So I think that on the one hand, it's exciting in that way. On the other hand, it's kind of like pulling something out of your ear and saying, okay, we need this new... Not only do we need dark matter and dark energy, we need some new other thing that's kind of like dark energy also, but happened only very briefly in the first 50,000 years after the Big Bang. Why did it happen? Why did it go away? We don't know. So that it's not, it doesn't have a compelling explanation, I guess, right now. And so maybe it's just waiting for the right person to come along and figure out why, or maybe it's just barking up the wrong tree.
Are there any testable hypotheses for that?
Yeah, so this microwave background radiation that you talked about, people are making better and better observations of it. It's one of the best sources of information we have about our universe, and that's because it's kind of this snapshot of the universe at very early phases. It really can tell us a lot about what was in it. And we think that some of the newest telescopes that are looking at this, or some of the data releases from the newest data releases from the telescopes, would be able to say if this stuff was there, we'd be able to see that signature in the sort of newer observations. So that's why I think in the next year or so we should know if this is a viable explanation, that basically we should see evidence for it in our telescopes, and it's good to have experimental evidence or something for sure.
I do want to try to define or at least go over the different, or I guess the timeline from the Big Bang to the cosmic background radiation and then these dark ages until you get the first stars. Could you go over that? And
yeah. Sure. So the Big Bang model basically says that everything was very hot and dense in the earliest phases, and at the highest level, the history of the universe is just a history of expansion, and with expansion comes cooling and then clumping with gravity. So gravity is sort of fighting the expansion to form the structures that we see. So the timeline would basically be that 13.8 billion years ago, we think, is when things started. At about 3 minutes or so after the Big Bang, it had cooled off enough that we were able to form the first helium nuclei in the universe at large. So that's called Big Bang nucleosynthesis, and it's one of the best tests we have of some of these models of what's in the universe. Because if you change how much, say, hydrogen is there initially, that's just what's there. Protons are out there, and neutrons, and some of them will merge together to form helium, essentially. And as the universe expands, there's less and less stuff nearby, and so it's less and less likely to do it. And so we can really measure how much hydrogen is out there, how much helium is out there compared to those observations. So Big Bang nucleosynthesis and its products, that's a really good way to understand the universe. And that happens for about 3 to 20 minutes or so. Then basically nothing happens for a very long time, okay? And this Big Bang nucleosynthesis, by the way, is happening when most of the energy in the universe is in radiation. It's not even in like matter or dark energy or anything like that. So the universe is what we call radiation dominated. It's just bathed in this really intense radiation. The temperature of the universe during Big Bang nucleosynthesis would have been about 1 billion degrees. So pretty toasty, much hotter even than the dense centers of stars. Okay, so it cools off, and the end product of this is something like 25% of the universe's mass ends up in helium nuclei, 75% in hydrogen. Nothing else is out there. So there are just 2 elements in the universe at that point. Then you just have to wait a really long time, okay? So nothing happens, and that's the dark ages. There's no light that's being produced in the universe. There's no stars. There's no galaxies. And the reason for this is that it's so hot and dense initially that everything is very homogeneous. Okay, there's only little differences in place to place of the amount of matter. So one place might have 100,000 atoms, another place might have 99,999, another spot might have 100,001. That's the kind of level difference we're talking about typically. Right, so very, very similar. But because there's this gravitational instability, the places that have that one extra will start to pull stuff together. The place that has a little less will start to spread out. And so the universe starts to get more and more inhomogeneous as time goes on. And that's once it's inhomogeneous enough, you can start to form galaxies. And so that's something where JWST has really contributed. Where are those first galaxies forming? We've pushed it back now to... There's probably forming maybe 100 or 200 million years after the Big Bang. So that's really when we can start to get astrophysical objects forming. And the first things to form are the smallest kind of clumps of matter. And then they continually accreting more and forming bigger and bigger things. So the first objects form out of just hydrogen and helium. And if they can form, then they can fuse to higher and higher atomic numbers and then get the carbon, the nitrogen, the oxygen, whatever, the stuff that we like, right, that we're made of. But the very early universe had none of that whatsoever. It really took stars and the deaths of stars to form that. So that probably happened, the first stars, maybe 100, 200 million years after the Big Bang. We've pushed back our observations with JWST to about 285 million years after the Big Bang. So we're now seeing stuff that happened back then when the universe was about 15 times smaller than it is on a side. Yeah, if you really think about the universe as a box, it's not really a box, but the universe has stretched out 15 by a factor of 15 in every direction since that time.
Yeah, so 15 cubed difference in volume.
Yeah, it's a big number, right? Yeah. So there's a lot more space out there. So that's where JWST has pushed back sort of our first observations to, and we're starting to see pretty massive and evolved galaxies then. So we know there must be stuff even earlier in the universe. But then as we push the timeline forward, those stars, eventually enough of them form that they become very bright and heat up the universe. So I guess probably I should step back because we skipped the microwave background, or I skipped it. That was my
That's
bad.
all good, yeah.
So, nothing happened after the first 20 minutes or so, but the universe is expanding and it's cooling. And by about 350, 400,000 years after the Big Bang, it was cool enough that that hydrogen could form as an atom. So before, you just had a proton and an electron. Every time it tried to form an atom, there were enough energetic photons that it would break it up. So light would break up every atom that would try to form. But at around 370,000 years after the Big Bang, you started to get atoms forming because the universe had expanded and cooled enough that light didn't have enough energy to split up the atoms now. And so what happens is that light starts to just travel freely. Before, it was bouncing around, off of all these free electrons. Now, once they're atoms, there's no free electrons. The light just travels freely, and that's what we're seeing is this microwave background. So it's really from 13.8 billion years minus 370,000 years. So really right after the Big Bang in sort of relative terms, and we're seeing then the distribution of matter as it looked then, and so that's what the microwave background tells us. So then really nothing happens until the first stars form. So we said the first stars are forming maybe 100 million years after the Big Bang. JWST is seeing back to 250, 300 million years after the Big Bang. And then by about 500 million years after the Big Bang, enough light has formed, enough stars have formed, and they're spitting out lots of light into the universe that it starts to heat up the universe again and then reionizes the hydrogen. So the hydrogen in between galaxies gets hit by all these energetic pieces of light.
So it's just floating around, super cold.
It's happy. Yeah. It was hanging out. Protons are hanging out with their electron friends, and then all of a sudden, these stars turn on and they spit out enough energetic light that it splits up those electrons and protons. So that's what we call reionization of the universe. The universe starts to ionize again. And we see today that the most of the hydrogen in the universe is ionized, and so we can actually see this. So that process takes a few 100 million years, and so by about 1 billion years after the Big Bang, that process is basically done. And then we can start to track, okay, galaxies get more and more developed, they get more massive, we can see bigger and bigger structures forming. We see the peak of when stars are forming is maybe 10 billion years ago, and so since then it's been a little bit less. You still see lots of stars forming, but the universe is spreading out, so it's just not as much vigorous star formation activity. Things aren't smashing together. It takes longer for gas to fall onto galaxies. Gas is the fuel for star formation. So, things have settled down a little bit now here, 13.8 billion years after the Big Bang.
Yeah. And then some of those stars, like you were mentioning earlier, have been around for a large portion of the universe's time in existence, I guess. And then some of the stars are in galaxies that have been around since really early in our universe. And some of those are on the fringe of the Milky Way, right?
Yeah, that's right.
What are you observing with these galaxies? What do they look like? Let's just start with that. Yeah. What are you observing and what do they look like?
So these are typically galaxies. The Milky Way is not one of the most massive galaxies in the universe, but it's pretty hefty. So its stellar mass is maybe 60 billion times the mass of the sun. So there might be, let's say, 100 billion stars worth of stuff. These are galaxies that are maybe a few 100,000 or maybe only a few thousand stars in them. So really, really tiny, dinky things, and we see them as tiny objects. They're also tiny in size, and they're also, if you look at what makes them up, they're mostly just this hydrogen and helium. So remember, I had said that there was just hydrogen and helium. Then as you start to form stars, they can spit out more elements, and so the subsequent generations of stars can incorporate those elements. So if we see stars that are mostly made of hydrogen and helium, that tells us they probably were formed really early in the universe because that's what the universe looked like then. And so we see these tiny galaxies that are mostly hydrogen and helium. They look very old, and and so they're just these tiny things. They're also the most dark matter dominated galaxies we know. So if you look at how fast the stars are going, they're going way faster than they should be based on the amount of light. And so there are just these dinky little things floating around that really look like they're fossils of the first few 100 million years of the universe. And the best theory we have right now is that cosmic reionization, when the universe heated up again, that's what shut them down, because there's so little gravity in them. I mean, there's more gravity than we expected, but it's still not very much. That when all that light came in and it heated up the gas, it just kind of boiled it out of those galaxies. And so now there's just no more gas for those things to form stars with. And so they just sit around like that for mostly the age of the universe and for us to observe today. So it's, for me and for a lot of people who work on this, it's a really cool set of galaxies because, you know, they give us a fossil kind of view of the early universe. These are really things that are just have been evolving in kind of isolation, not forming stars. So it's a fossil record of the earliest phases of galaxy formation. And they're these dark matter dominated things. So they're really telling us about dark matter. So they're pretty interesting galaxies called either dwarf galaxies or ultra faint dwarf galaxies, especially, are the ones that are the sort of most dark matter dominated, the lowest mass, the ones that are sort of the most primordial looking.
I love the Indiana Jones comparison you give to yourself with the cosmic archaeology.
Yeah.
Yeah. I don't know.
I can't pull off the
chuckle.
fedora, but you know, yeah, trying to really do it is archaeology, right? We're really looking at the sort of remnants of the distant past in the nearby universe, and then we can compare to direct observations with James Webb Space Telescope. But one of the benefits of looking, you know, at the nearby stuff, well, first of all, it's easier to see stuff that's nearby. And you can just, it's, you know, cheaper, and we can see a lot more of them, right? And so these are things we'd never be able to observe directly with James Webb Space Telescope, but we can see what they would have looked like and even reconstruct that, just like you can reconstruct ancient civilizations by looking at pottery shards or whatever that you're finding in the ground. So same idea, yeah. So Indiana Jonesing it up for sure.
How far away are these galaxies from? I mean, you mentioned that they're close.
Yeah.
How far are they from the Milky Way?
Yeah. So the Milky Way itself is, well, we're sort of about 20,000 light years from the center of the galaxy. And so some of these might be, the closest ones might be a factor of 5 further away from us. So, you know, 100,000 light years away from us, out to maybe 1 million light years away from us that we're observing. And that sounds really far, but these galaxies we're seeing on the other side of the universe, they're 20 billion light years away, 25 billion light years away. So these things that's 1,000 times, you know, further, 10,000 times further, right? So in astronomer terms, you know, a few 100,000 light years is nothing compared to the size of the universe, yeah.
So why don't those tiny little galaxies get sucked in and incorporated into our Milky Way?
Yeah, that's a great question that people have thought a lot about and kind of studied. You know, some of them do probably get sucked into the Milky Way and shredded, but when they fall in with a lot of energy and a lot of angular momentum. So just like, you know, when a figure skater is twirling and, you know, if they pull their arms in, they twirl faster. Same thing with a galaxy like this. So it goes a lot faster near the center. So unless there's something that slows it down, makes it sort of stop near the center, it can just come back out of the other side. So the thing that could make it stop is maybe hitting the galactic disk or something like that. But a lot of these just orbit around, and there's nothing to really slow it down. Now, more massive things, the mutual gravity can kind of slow it down. But these things that are so low mass compared to the Milky Way, they don't really slow down because of the gravity. So they just sort of zip around almost for forever. Yeah.
That's pretty cool.
Yeah. You know, we didn't know about a lot of these for a long time. You know, the first ones were discovered in the 1930s. And then there was a big revolution in the 2000s. And, you know, we sort of went up by a factor of 5 or 10 of how many of these galaxies were known around us. And we're thinking that this Rubin Observatory that is starting in next year will really discover a bunch more of these and really help fill in our picture of how many of these little shards of galaxy formation there are around the Milky Way.
Yeah. And what's keeping those galaxies together? Is it the mutual gravity of all the stars? Dark matter? Do they have the black holes of their own?
So yeah, good question about black holes of their own. Definitely, we don't know that. There are some claims of black holes and individual ones, but I think nothing definitive right now. We know there'd be black holes from the depths of individual stars, but that wouldn't be like very massive black holes. At the center of our Milky Way, there's a black hole that's about 4 million times the mass of the sun. So we don't think there's anything like that out there. But Carl Gebhardt, one of the professors in astronomy, thinks he's measured something that's that massive in one of these, which is a really cool claim that people are trying to look into. Right, and just like we talked about with like planets going around the sun and stars moving around in individual galaxies, we can try to figure out how much mass there is based on how fast these objects are moving around the Milky Way itself. And if it was just the mass of stars of the Milky Way that was pulling it in, or stars and gas, that wouldn't be nearly enough to have these things stay around the Milky Way. They'd shoot off to infinity. So we really think it's got to be the dark matter of that's surrounding the Milky Way. So we think every galaxy in the universe has a halo of dark matter that kind of surrounds it. And that's actually how those galaxies form. The dark matter sort of collapses up, not a huge amount, but gives a bunch of gravity, and then the gas falls in, and then it can really condense to the center of that dark matter halo. And so these things are all orbiting. They have their own individual dark matter halos around them, and those are orbiting within the Milky Way's bigger dark matter halo.
That's really cool.
Yeah, so it's kind of like, hills are on mountaintops or something.
Yeah. That's a good analogy. What exactly do you mean by halo? Like an actual like angelic looking halo?
Yeah,
or?
so in this case, you can really think of it as kind of like a diffuse ball of dark matter. So it's a halo in that sense, just this sort of like ethereal. So it wouldn't be a ring for sure, right? That you see clearly around my head. No, so it'd be more like a spherical ball around it, where it's denser at the center and less dense at the edge.
Look like a cotton ball or something.
Yeah, basically.
Okay.
But it would have a lot more density towards the center because it's really held up by gravity.
So why do galaxies not form in that way? Why do galaxies have this kind of spiral, almost like solar system looking shape, kind of flat disk, but dark matter, it seems like you're saying it's spherical. It's like almost like packing itself.
That's right. So there are galaxies that are spherical, so they're elliptical galaxies, but you're right that there are a lot of galaxies like our Milky Way that are very flat spirals, right? They look like dinner plates sort of spinning or whatever. And the reason that they can do that, we think that dark matter can't, is that they do interact with light. They have these interactions that dark matter doesn't have. So the gas is able to cool. Dark matter doesn't have any way of cooling. And so when it cools, what it can do, that makes it go down to smaller and smaller scales. And then eventually that'll collapse in one direction into kind of a pancake. And then that pancake can start spinning, and that spin comes from that same angular momentum I was talking about with the figure skater. So regular matter conserves angular momentum as it collapses, and so we think that the dark matter gives it that angular momentum, and then it starts out as a ball, but any slight difference in one direction compared to the others will mean it'll collapse up along that dimension and then start to spin in that way.
Does dark matter behave similarly, where like I know our sun is constantly spinning pretty fast, and so I'm gonna imagine if you have like a galaxy-sized, I don't want to say star, but like star-shaped thing, but like this huge spherical ball of dark matter, would that be rotating as well?
So as far as we know, that doesn't really rotate. Basically what happens is particles are coming in from all directions, and there might be a little bit more that comes sort of in one direction from another. And so in the net, that means maybe there's 1 billion particles going this way and 1,500,000,000 going that way. And so there's a little bit of net rotation, but in general, it's not like everything is going in one direction. Mostly it's just stuff going at random, but there's a little bit more going one way. So on average, there's a little bit of general rotation, but they're mostly not rotating.
Yeah, that almost seems more like deformation of the structure itself and less so like a nice homogeneous rotation.
Yeah, for sure. So you can almost think of dark matter as initially kind of just being a sheet, and then that sheet is just bunching up into different spots, right? And then, and so some of it, maybe there's like a 5% difference one way versus the other way, but it's really, it's not coherently rotating exactly.
Okay. But
the gas does start to coherently rotate. So it picks up that 5%, and then the whole set of it will go.
That's really cool. So it's like transferring angular momentum.
Oh, yeah.
But it's not really homogeneous. So it's not tightly packing itself like observable matter is.
That's right. So, there's no way that dark matter has to cool off like regular matter does. Regular matter, atomic matter, cools off by emitting light. Dark matter can't emit light, so it can't cool off. And so, a particle will come in and it'll just go faster and faster and then zip out. And, it reaches some kind of equilibrium. But that means that there's more in the center, but it's just never gets to be a very, very dense center. Whereas regular matter like us is extremely dense compared to the universe on average. So we usually talk about a dark matter halo. It's something where when you take all the mass and you take the volume that it's in, that density is something like 200 times the density of the universe. If you ask how dense are we or water or something like that, it's 10 to the 30 times the density of the universe. So our stuff is way denser than dark matter ever gets.
Yeah, to get to the same density, or I forget exactly what you were trying to upscale or I guess downscale the density of Earth to, but it was to get it to the same density as some kind of body of dark matter, you'd have to stretch the radius of Earth to the next closest galaxy or something like that.
Yeah, you'd have to basically go to the nearest star, right? You take the Earth and you go out to, it's probably the sun actually. You take the sun and go out to the nearest star. So you spread it out that much. That would give the same density as a typical collection of dark matter in the universe. So that'd be pretty far, right?
Yeah. What does it mean for dark matter to have to cool off? Are you implying that it has temperature, or?
Well, so it has some kind of energy, right? And so the individual dark matter particles, they don't have a way of changing that velocity, let's say. So normally in physics, there's a temperature and velocity are kind of equivalent. You can say the temperature goes like the velocity squared, and so here there's just no way of changing that average velocity. So there's no way of changing that average temperature of an individual particle. So if I have a ball of hydrogen, it can just emit radiation, and the whole thing will cool off. If I have a ball of dark matter, any one particle might cool off, but another one will heat up. And so there's no way of the whole thing sort of releasing energy that way.
And is that why the collision between two dark matter particles gives off so much energy, because they have so much energy to begin with?
Well, that definitely would be related to, if things do hit, then something big would happen there.
Yeah, I'm trying to sponge it into my brain. It's a lot.
Yeah, I have trouble sponging it into my own brain, so I don't. It's impressive you've already got all this stuff under your belt. That's pretty cool.
Yeah, thank you. So you seem to like to define yourself as a theorist.
Yeah.
And I'm curious what kind of the process of studying science with that perspective is, compared to someone who's more of an observationalist, someone who works with a lot of data, someone who, like at Georgia Tech, they do a lot of those black hole simulations. We do a lot here too as well, but it's like a different kind of approach that you have to it, because you're really trying to pen and paper, think of new novel things, right?
Yeah, I think that there are definitely differences. A lot of the base is the same, right? You need to understand a lot of the same physics, a lot of the same math. But then people who either, say, build instruments or do observations, they need to understand a lot of specifics about those instruments they're building, how to do the observations, all of that. Whereas I'd need to understand maybe more details about some of the physics or the math. And then again, it's sort of what are the questions that you're asking, right? And so we get this interplay between us and the observers and the experimentalists of, I say, what if I change this about our models of the universe? What would the observable consequences be? And then the observers can go out and measure that, or they can say, hey, I went out and measured this. It doesn't match up with your models. Go figure out why you're wrong, and then that's a fun thing for me to come back and say, okay, why would the universe look different than what we thought it did? And a lot of it does come back to, what are the questions you're asking, and how are you trying to back that up with the models that you're building.
Okay.
And you mentioned pencil and paper. I try to do some of that, and there's just a lot less room for that than there used to be. People have done a lot of it, so a lot of the tools now are supercomputers. So most people who do theory, myself included, are spending a lot of time running simulations, either sort of smallish scale, but sometimes up to using tens of thousands of supercomputer cores at a time, and sort of equivalently taking millions of hours on supercomputers. So not millions of hours of the day, but if you add up all of the processors, how long they've taken, millions and millions of hours producing terabytes, even to petabytes of data that you have to go through to look for some of these signatures. And that's why I think people started to get interested in AI and other things like that, to kind of understand, would that help us sort of sift through things? And I think there are a lot of great possibilities there, but I think the one thing AI can't do at this point is to know what the questions are to ask, and I'm not sure they'll ever know. And so that's really where I think developing one's intuition and focusing is always going to be the payoff, knowing what are the questions to ask. And that's not just in science, right? That's everywhere. I think knowing the questions to ask in business, in social sciences, all of that, that's the hardest thing, right? It's not, if somebody tells you, go do this, that's going to make you $1 million, you can do it, right? But it's that, what's this? How do you get there? And that's always where humans are needed. The machines, you can tell it to do things a lot faster. You can tell it to do this new fancy analysis on it, but you have to know what you're telling it to look for. And I think there have been advances in sort of pattern recognition in computers that are maybe sort of going a little bit beyond just getting the instructions and doing what we've told it, but I think it's still not at the point where it's knowing, here's what we should be looking for, right? And that's what we're trying to do as scientists.
Yeah, it just knows the probability of what word it should say next based on, some huge training set of, a couple billion questions that have been asked before it.
Yeah, and I think it's one thing if you want to say there's a 99% probability that this is a sentence in the English language. Of course, if you want to do something that's going to stand up in a court of law, you don't want it to be 99% chance, right? Or there's certain things where you don't want that. In our field, it's really good at, again, pattern recognition or image processing, things like that. That's something where probabilistic models are really, really helpful. Or it can sort through a lot of data and say, hey, here are the things that might be interesting, and then you can follow up on those yourselves. And so there are a lot of good, I think, as this sort of middle layer, it can be amazing, the advanced computing. But I think it's not replacing the need to have the people, A, to ask the right questions, and B, to figure out what the final answer is. Or maybe C, if there's a B in there for the AI.
More so augmentation than replacement.
Yeah, I think that's right.
Yeah. It does seem really interesting how physics has changed over time, because you started out with like Newton and, the apple falling on his head. Whether or not that was a true story is kind of besides the point. But he's trying to model stuff that he sees with his eyes, or stuff that he can observe and experiment mathematically. And then you kind of continue that approach with science and you sophisticate it more and more and more. But now we're getting to a point where we have so much data. They didn't have that much data to work with back then. And it's interesting. I wonder how physics is going to evolve from this point onward.
Well, yeah, I think that's a great observation. And it's, for particle physics, it's been in this difficult situation for a while now. I think sort of like you're saying with Newton, he was able to the data he could take, he could come up with theories that would match the natural world. And for a long time, it was trying to catch up to, okay, we've seen all this stuff. Now, can we make this, reproduce this? Particle physicists, after a while, they were able to do things so well. They were making predictions about things that hadn't been seen, right? So they predicted new particles, and they smashed things together and started to see those. But now they've made these models that are so good that we can't even smash things together at high enough energy to check out their predictions. So there's almost, what is the next level of trying to get to that knowledge? How can we get to new knowledge there? And I think that is a good question. What are the questions that we ask, and how can we get to experiments that can actually test those questions? And I think it will be interesting to see what is meant for particle physics, and also now for astronomy, is building bigger and bigger teams that are doing things, right? So the experiments used to be one guy in a lab, right, and with some assistants, and now it's every paper that's at the cutting edge of particle physics experiment typically has hundreds or thousands of people who have contributed to it, and they're all co-authors on that. And astronomy now also has frequently hundreds of people on an individual paper, because it's taken that many people to get to that point, whether it's planning the observations, writing the software, doing the observations, analyzing that, interpreting it. There's just a lot going on. And, I think people always have to ask themselves, is that the kind of field do I want to be in, right? It won't be sort of one freewheeling person sort of, with a pencil and paper and sort of saying Eureka probably as much anymore. There's still some space for that, but it's a lot harder. But I think there are still fields where there's a little bit more of that, and so people who are drawn to that sort of science might think that's the field to go into. But sometimes you just get the call of the wild, right? And you want to study the universe or exploding stars or whatever, and then that's what you do.
Yeah, there's so much innovation in like you said, like how we're doing these things, and it's getting so interdisciplinary. And there's this whole new skill set of trying to work with supercomputers, because they're so important. But I've taken a couple physics classes with astronomy majors. I'm a geophysics major myself, so I don't have so much experience with what classes go into that major. But it doesn't seem like they're taking classes that are like how to write good software for parallel processing of this huge, million GPU supercomputer. And I know that a big complaint of complaint's a bit of a strong word. He'll tell you himself. I talked to the director of the TACC about a week or two ago, and his big problem with the whole evolution of supercomputing and high-level computing in science is that the hardware is super good and everything's getting really good, and the machines are amazing. There's so much money going into it, but no one's writing good software. Yeah. Right?
No, I think that's very true. People who are doing this are typically trained as physicists or maybe math, astronomy minors essentially, or majors, but it's not something where you've learned from the ground up, here's the best way to do this coding stuff. And I think part of that is that there's just no way to get all of the background and all of these things. But it is a problem. And, I think that just like the experimental side of things has taken these bigger and bigger collaborations, now the theory side, the computation side, will have to take those also, where you start to have people who are really specialized in understanding the algorithms, and they can work with people who understand the physics you want to implement on the algorithms, and then you can really get those people working together, because there are a few unicorns of the people who really are good at the computing side, who even people who work on computers would say are good at the computing side and good at the physics side. But it's usually people who are not trained at all in that computing end of things who are then thrown into trying to learn that, and probably aren't using things as efficiently or writing code as well as could be the case.
Do you find that there's a demand? So let's say within the College of Natural Sciences, when you're hiring a new postdoc or a new faculty member, are they trying to really look for a lot of experience with computational science or like programming experience?
I think that I think it's a little different for postdocs and faculty. For faculty, usually it's, look, are they asking interesting questions? Are they producing interesting science? And a lot of times that it does require experience in the computing. If, I'm hiring somebody individually because I have a federal grant to do something specific, then definitely I don't want to, the period of that postdoc is usually, say, 2 to 3 years, maybe 4 years. There's not enough time to learn all the stuff you need to know and then apply it to the science, right? So you really do need somebody who's got that skill set coming in. And so that's why it's so valuable to have those computational skills, because then you're head and shoulders above people who might be just as smart and just as energetic, but there's just not that amount of time to learn it and be able to apply it in the period that you have for your employment.
Yeah. And I guess just more of a fun question. Do you ever think about, when you're making these observations or when you're trying to think about dark matter in these galaxies, just how small we are? Just in space, but also in time?
One of the things that I think is fun about this job is that, like, you can get lost in the work and not think about that at all, right? In the day-to-day, you're just writing these numbers out, and you're saying, okay, it's 100 trillion times the mass of the sun.
Just throwing around these
huge,
yeah.
A billion of these in the unit. And you have that in your head, and you're just working with it. But then you step back, and you're giving a talk, you're teaching a class, and you're really trying to put it in context. And then you say, oh my gosh, this is wild, right? Like when the first nuclei were being fused, the universe was 1 billion degrees outside. It's pretty toasty, right? Or we're so small compared to the size of the universe, or our lifespan, like you're saying, is so short compared to the age of the universe. But I think that if you spend all your time thinking about that, you'll never get anything done. There's just so much cool stuff out there to think about that if you just spend your time sort of pondering how much cool stuff there is, it's hard to get anything done, actually. So I try to not spend all my time being amazed by all the cool stuff out there, sadly.
That's a great way to think about it. There's such a good quote somewhere. I forgot exactly who said it, but it was like, the man who thinks all the time has nothing to think about except thoughts.
Yeah, that's I think fair.
It reminds me of that. What do you think about aliens? Do you think there's aliens out there?
I go back and forth. I used to be pretty convinced there have to be. There's so many stars, there's so many galaxies, that how could there not be? But then the other argument is maybe the conditions for life to form and then to get to intelligent life are just so rare that even if there are that many planets, it doesn't really matter. You'd really have to get super lucky. And the fact that we haven't, come across intelligent civilizations, that we know of, or that are believable, demonstrations of that might mean that life is rarer than my first sort of instincts would have said. And so I've sort of thought of it both ways, and I think that's why it's really exciting that we're sort of pressing out to bigger and bigger scales with these bigger telescopes to really start to ask, okay, is there a bottleneck somewhere to forming intelligent life? Is life common throughout the universe, but it never gets intelligent or super intelligent? And I'm excited to find out the answer. I hope we get to see that in my lifetime, and I think that's really a cool possibility. And it'd be awesome if we're here on campus and can hear that UT astronomers have discovered intelligent life somewhere else or something. That would just be amazing.
That would be world shaking.
Oh yeah, and I think that's something that is not just for astronomers or physicists, right? This is what philosophers and biologists and all kinds of fields have been thinking about forever. Is are we alone in the universe? What's out there? What does consciousness mean? Things like that. They're just a ton of deep questions, and I think it shows how it's all kind of connected. You have to know about the geophysics of some of these planets to understand some of the observations, right? So interdisciplinary stuff, people like to talk about it as a buzzword, but it's really there for a reason, right? The bigger the questions you get to, sometimes the more you need to synthesize to get the right answer.
Yeah, I agree 100%. Is that kind of pioneering, like wanting to discover the unknown, what's out there, your motivation for astronomy and astrophysics? And
Yeah, I think understanding at some level is one of the motivations. I always thought, or always, I mean, when I started getting interested in it, I thought it was really cool that the physics of the very small, the quantum mechanics, actually governs the physics of the very large. The structure of stars is set by quantum mechanics, right? Why is the smallest stuff in the universe connected to the biggest stuff in the universe? That just kind of was mind-blowing to me, and I found myself wanting to understand that more and more. So I think, getting that understanding and sort of that insight is addicting isn't quite the right word, but there is like a real rush when you figure out something, all the pieces kind of lock together, and you're like, oh yeah, that's why it's like that. That's pretty cool, and so that's a great motivation, I think, for doing stuff.
yeah. And so has that motivation stayed constant through time? Is that like the hedonistic kind of like, what could be out there? And then you kind of figure it out. It's almost like a hydra. It's like the more questions that you answer, the more questions that you have.
Yeah, I think, but it does stay there. Once you get that thirst, sometimes it's hard to get rid of it. And now I have probably a little less time to chase some of those questions, but I also have more knowledge, so maybe I'm able to get at certain things that I wouldn't have been able to get at before. And I think having students and postdocs seeing them like get that same, oh man, now I can really ask this question, now I can tackle that, I can see how these pieces fit together. That's super cool. And I think that's where a lot of the exciting science is, like we were just saying, at the edge of the disciplines, or looking at two things that seem kind of different or disparate, but really understanding there's some deeper connection. And that's where I think having that sort of grounding in a broad understanding can really be helpful.
There seems like this inversely proportional relationship between the amount of time that you spend in science and then the amount of time that you can actually spend on science. Like you get busier and busier and busier, and then you really have to start worrying about pulling in money for your specific program and getting the right postdocs, getting the right students, trying to mentor the students, and then all of a sudden you find yourself in a spot where it's like there's so many curiosities that I could have, there's so many things I could do, but I just don't have the time to do it. Yeah,
definitely. And I think a lot of times when people are undergraduates or even graduate students, they worry, okay, if I go into this field, will I have enough ideas to like really sustain me, right? Because you're sort of starting out usually doing what somebody has suggested to you. But I think pretty much universally what people find is there are way more good ideas you have than time you have to pursue those good ideas. And so sort of that selection, that editing of oneself is important, trying to figure out what are the important questions, what should I be working on. That's a hard one, and people are always asking and talking about how do I figure that out, and there's no good answer. There's some instinct, there's some trying to figure out what other people are thinking about. Sometimes you want to go that way, sometimes you want to avoid what other people are thinking about, right? You want to think about different stuff. But there's way more good questions than there are times to to address them, which is probably a good thing at some level.
Yeah, maybe AI can help us with that.
All right, yeah. Any help I can get, I'll take it. Yeah. No, I think that, I think AI, there are definitely going to be some spots where that can help. And I think, being at UT, there's a lot of cool applications of that. And it's great to have a good computer science department, and one of the top ones for AI, and other like the Odin Institute and things like that.
Stenzione was telling me how he went to the director of CNS, or like the dean of CNS, and he was like, hey, I need like this amount of money for this new AI project. And he was like, oh, AI? And he gave him twice the amount of money that he was asking for.
That's pretty cool.
Yeah.
Yeah, there's a lot of money out there floating around, isn't there?
Yeah.
I just saw that, today the stock market's way down, but anyway, in the last month or something, $2.6 trillion of, the top seven, basically, Microsoft, NVIDIA, Apple, all those, market cap has been wiped out. And that tells you how much money is in there, and they're all pursuing AI heavily. And I think, the question about commercialization is separate from the question about its fundamental applications. And, how useful will it be for my refrigerator to be in contact with like my car? I don't really know, right? Like predictive, do I really want like my toilet to tell me you're going to need new toilet paper in like 3 months? Like that's not super exciting to me, but there are lots of cool applications potentially.
I don't think I want my toilet registering any
right.
information
Right.
from what I'm doing.
That's right, exactly. So let's keep that between us.
Yeah. Do you find AI to kind of be so? From my perspective in geoscience, I've been to a few conferences, and it seems like most of the posters in the poster hall, 60% of the posters in the poster hall have something to do with AI. Like everybody's trying to jump on it. Is it the same with astronomy, do you think? Like everyone's trying to jump on this bandwagon and see how they can apply it to the science?
I think that's definitely the case, that especially for sort of, some subsets of AI, or maybe machine learning is a big deal, and a lot of people are thinking about that. And to me, it's one of those things that, again, it's a tool, right? And once you have that tool, it's sort of like everything looks like a nail if you've got a hammer. Yeah. And so I think I worry a little bit that people have this tool and they're just trying to address every problem with that tool rather than thinking about what tool that problem requires. But on the other hand, once you have a really powerful tool, it can be helpful for that. So, but I do see a lot. There's a ton of machine learning that people are working on and applying to astrophysical problems and even AI itself. Yeah, I mean, a little less sort of large language model type stuff, but yeah, there's a lot of applications that people are doing now.
Yeah, it seems like in your case for astronomy, it would be more image processing like AlexNet or something like that.
Yeah, there's a lot of image processing. There's a lot of, just sort of trying to take, you have these sort of problems where you can say, I assume some initial conditions. How can I model it forward to match the observations? Or how do I take observations and then model it backwards to say what's the underlying physics? And AI can kind of do both of those, right? If I have two distributions of dark matter, can it tell me which one came from an underlying physics model of what the dark matter is? So that, I think, that's a place where you could really see this going well, hopefully. And I think that's a place where I'm involved a little bit in this. I wouldn't say I know much at all about it, but that's a place where I've been kind of interested in sort of either these forward or inverse problems. And I think that's the place where things are really promising.
Yeah, it seems like every conversation nowadays leads to AI.
Yeah.
Once you talk for long enough, then you start talking about it. It's like all roads lead to Rome.
Well, there may be a sad lack of regular intelligence, and so we're substituting artificial variants.
Yeah, I think the really exciting thing for me with AI is it's seeing correlations that you can't see. Like your human intuition just can't see that because, or like the causation has so many different steps to it, and there's so much mental gymnastics you would have to do, and but AI can just see it. Right. Like it just sees the trends in data because it looks for different things because it doesn't it doesn't really care. A good example is a guest I had on the podcast. He was talking about how he would use these large language models and these algorithms to try and create targeted ads. Mm-hmm. And he was finding that, or I don't think he found it, but they found that people who bought a lot of diapers also bought a lot of beer, or like they were like very likely to buy beer. And it's like, yeah, when you think about it, you could start to do some mental gymnastics as to why that's the case, or maybe inverse. But it's not something you would think of right off the bat. And if you had the data in front of you, I don't think you would really, it would take you a long time to find that correlation.
Yeah, I think that's true. But again, I still think you'd have to, I don't think it won't just say I'm going to look for this, right? Like you have to tell it to kind of, so there's Exactly. Still that human element that has to, point it in the right direction, and then it's going to do stuff that you can't do, right, for sure. But you still got to somebody's got to be there to point it in the right direction still. So you still have to know what the questions are to ask a little bit, and it can get you there a lot faster. It can see stuff that you can't see, but you still have to tell it what to look for, I think.
Yeah, the wild thing with ChatGPT and these huge language models is that they have to be told in some kind of command prompt or like super prompt. I don't know the exact right word. Super prompt is very non-scientific, but they basically have to be told before they give you any answers that what they are. You're this language model that's supposed to help us out, and you have to be very nice, very friendly. If anyone says anything mean to you, just like, because if you don't do that, then they start just like spewing out all information, like, because they're just spewing out information based on the stuff that they read and basically the internet, right? And the internet is just full of cesspool. Yeah. So they're just spitting out what they think is best, and so they'll spit out really wild stuff.
Yeah, and I think that's a worry for the science applications, right? Because if basically your training set is the existing set of data, how can you ever make a real advance based on what's already known at some level? And maybe can you fundamentally change things, or are you only just going to improve on things that are already there at some level, like refinements? And I guess we'll see. I'm not sure that there's been any singular discovery that's been like a field-changing discovery that's been made by AI at this point. So I'd be interested to see whether that happens, right? Whether it can come up with, here's a new theory of X, Y, or Z that's totally different. I'm not sure it's optimized for that at this point.
I think it'd be really cool to throw it at like older data sets and then see if there's anything that we kind of, because we're always focused on, okay, what's the next telescope? James Webb. Oh, okay, let's make an even bigger one in Chile, or let's make this like a massive one in Europe. And then most of the community is probably going to be focused on the new data that you're getting, and the people that you're throwing at the old data sets is like undergrads, grad students, people that can like have the time to kind of sift through it and find correlations where they can. And that seems like a good use of computational power for AI. Is like, what about these old data sets? Are there any correlations or weird things that maybe we're not totally seeing?
I think that's a really good insight even beyond AI. I think that we're very quick to want the newest and biggest thing, but there's a lot of data out there that were taken for one reason and maybe applied to something slightly different could be transformational, right? You just need to know, is that data set out there? You needing to know what question to ask with it, right? It was collected for this reason and it's just sitting there, but if you said, hey, wait, I could connect that to this other data set, you don't need to just come up with a new one. And we do this a lot in my field still. It's, you want to run the biggest new simulation, whatever, but there's a lot of mining of older simulations that would be very valuable, I think. Yeah, so I think that's a great point.
Yeah, like being creative with data seems like such a valuable skill.
Yes. Yeah, and I think that's, sciences, even beyond, in finance, whatever, business, any of these things, like people are being creative. Creative is something that is always a good thing, I think. I think that's always a great compliment when somebody's like, oh, that's a really creative idea or solution or whatever. I think like I'm always happy to hear that about my science when that's rarely when people say that to me.
Yeah, I mean, it really does, especially with these huge missions or these huge projects, it seems like it does turn into almost like a geopolitical economics problem, because you have one instrument and tens of thousands of astrophysicists, and then probably millions of people that are tuning in or reliant on the discoveries of those astrophysicists or astronomers and astrophysicists who are all lined up to try and get their project on this telescope, right?
And it's a complicated process, right? And it's like you say, there's a lot of people who want it, and it's a limited resource, and so time allocation is a big deal, right? But I think that's why you try to make these telescopes as multi-purpose as you can. And one great thing about astronomy has been, you're not just building a machine to find one number and then you throw all the data away and never use it again. People are building these machines to look at things we've never seen before, and then that leads to all kinds of new questions, to new knowledge and all of that. And it's a kind of a different way of doing science, is to just, hey, let's build this and let everybody figure out what to do with it, versus, hey, let's build this to do this specific thing. And if other science happens, that's great, right? And I think that, for example, the particle physics stuff, that's a lot more, we need to build these bigger colliders that will collide particles at a higher and higher energy, and here's exactly what you need to do to build that, and here are the 3 questions that you could ask about it. And people come up with clever other things around that, but it's a little less like, I don't know, likely that you're just going to find something totally new. Whereas when you look at a new part of the electromagnetic spectrum or further out into the universe or use gravitational waves that you've never seen before, there's always stuff that's unexpected and that you've never seen. So we're pretty lucky in astronomy in that way, I think.
Yeah. Yeah, I bet you, I mean, you tell me, but with supercomputers, like the huge problem is that there's so much compute power, but you have to know how to use it creatively because like at Meta, for example, all of Meta's like GPUs, all their computers are running, but I think it's like something to do with the latency or something to do with the software they have to where like in some of their computers, like 50% of the computational power, 30% is basically being unused or not used efficiently. And I would imagine it would be similar with the telescope, like with these huge international collaborations, let's say with James Webb or something. It's like, okay, how can we find a middle ground to where we can observe? There's probably a whole politics of like which section of the sky should we observe?
Oh, yeah.
And then, how can we observe the right section to where, we can make party A, B, and C all happy and all have an observation that is useful to them.
Yep, definitely. There's a lot of politics that goes into all of this now, and I think it's definitely true for the supercomputer stuff, and that's one of the reasons, like you were saying earlier, that you want people who really know both the science and the computing side of things, because, for example, when some problems work really well to say, I've got 10,000 processors, I'm going to farm this out, they're all going to crunch things together, and we'll just merge the number at the end. That doesn't work for, say, gravity, like the simulations I do. All the processors have to be talking to each other a lot. And so that's a different machine design that you need fundamentally, right? You need to have lots of communication, so you need the networking to be really strong. You might need lots more memory to hold numbers in memory as they're doing this communication. And so that's why talking in between, the computer scientists, the people who are at TAC and the scientists who are doing the applications, you need to figure out what do you need. And so I think it's important that we're always talking, and by we I mean somebody else again, high above my pay grade, but it's really important that people who are directing, the National Science Foundation or sub-directors of that can actually get together and say, hey, here's how we can make machines that are going to work well for everybody.
Yeah, I mean, that's what a lot of Dan has to do, and I bet you have to do it too. Like you're walking on the fence between multiple worlds at once. I can imagine you would do that just in astrophysics in general because you have all these different, branches of it. You have the, theorists of the quantum mechanics theorists. You have all the string theory people. You got
how stars are formed. Galaxies.
Exactly.
Yeah, definitely.
So you have to walk between those worlds, but then when you're involved in these supercomputer projects, you have to know the code, or if there's somebody that's helping you write that code, you have to be able to talk to them, and they have to be able to tell you what they're doing, and you gotta
talk the same language.
Yeah, exactly. That seems to be such a big thing. Like in geology, for me, there's so much jargon, and even in so if someone studies volcanoes, there's a completely different subset of jargon than if someone studies glaciers. Right?
Studying glaciers and volcanoes sounds amazing, by the way. I'm excited. Geoscience sounds really cool.
Yeah, thank you. I appreciate it. I think studying this is absolutely fascinating because you're at the precipice of what we know about the universe. We have no direct physical observations of dark matter, right? It's just implied by the physics and simulations that we have. And now you're at this point where it's because of this age discrepancy, we might have this even new thing. It's really cool to see that. And then on panels like Neil deGrasse Tyson and all this stuff. But it seems people are really fascinated by astrophysics. I feel like it's a really popular, more popular than a lot of other forms of science.
I think we're kind of lucky as astrophysicists in the sense it's one of the few areas where everybody can look up at the night sky and wonder like what's going on out there. How do we make sense of our place in the universe, and like what's beyond, and what are the rules that are sort of that we're all subject to. It's sort of this universal experience. So I think that's one really cool aspect. And I think the other thing is we just have really pretty pictures of the sky, right? I mean, I think there's a ton of tremendously interesting, exciting stuff in biology, but it's just hard to make a pretty picture of like a bacteria to compare with some of the stuff you can get from astronomy potentially. I guess that's all subjective, but for me, that's always been one of the cool things is you can just sort of, there's this universal human experience of living in the universe, right, and trying to make sense of that.
What's really cool to me is the compilation of images of our universe from, James Webb or Hubble, that a lot of the gas formations or stars or things like that look like biological features.
Yeah, it's pretty amazing, isn't it? You get sort of like galaxy distributions look like neurons, and some of the galaxies themselves look like certain cellular phenomena. So there are these like, yeah, on different scales in nature, it shows up. It's kind of amazing.
Yeah, I always hear this quote that we are the universe taking sentience and then looking back in on itself and trying to understand itself.
Oh, that definitely sounds above my pay grade.
Pretty meta.
Yeah, for sure.
And yeah, you could start to spew out crackpot theories all day about what the universe is.
I can definitely spew out a lot of crackpot theories for sure.
Yeah, what's your general take on I guess as an astronomer and astrophysicist, maybe not why are we here, but what even is this,
I don't really have a great take on that, but I do think that the thing is, like, it is what we make of it in some level, right? Like, no matter what's out there or why it's out there, some of these questions maybe we'll get an answer to. I don't think we can, but they're questions that we can impart value to, and that we can, the fact that we're here and that we're able to ask these questions, that we're able to do some of these things, that's what's we should be taking away from it, right? Like that's what's amazing about it. And so I think we can put some of the value onto it ourselves, and not just sort of ask, why are we here? We can sort of create purpose, and I think that's pretty exciting. We have that agency, right, which is pretty amazing.
Yeah, I mean, we seem so lucky to even be here on this planet, just like statistically speaking.
Yes. No, and I think like, I got a couple of kids, and just seeing them grow, it's amazing. And just sort of thinking about all the things that can go wrong, that like things go right all the time. I don't know, yeah, I don't know, the word miracle is probably thrown around a lot, and maybe has imprecise meaning here, but it's just, yeah, there's a lot of stuff that feels amazing that it can actually work out. And like you said, that humans are here, that individual humans manage to make it through all the weird stuff that happens. Yeah, it's pretty cool.
Yeah. I saw this theory. I don't know how much real scientific evidence there is behind it. You'd have to tell me, but like some kind of change in the distribution or gravitational effect of dark matter at some point in our solar system, where there are a lot of asteroids, sent more asteroids than normal towards Earth, which is the reason that the Earth got hit by an asteroid 66 million years ago that wiped out the dinosaurs.
Yeah, there are theories about that. I think it's not 100% firm, but I think there are reasonable possibilities that these things that we think are unconnected to our daily existence are really fundamental for it. I don't know if this particular one is true or not, but I think that there are a lot of these cases where there are connections that we don't think about, and I think again that's kind of where the exciting stuff in science is, looking for these unseen connections and trying to make those.
So when you're thinking about dark matter's effect on the macro scale, how much do you have to scale up to see that? Because I was just talking about like maybe an effect on an asteroid belt somewhere. can we see effects of it in our own solar system, or do you have to really zoom out?
Yeah, we would not see any effects of dark matter in our solar system at all, sadly. I mean, it basically just looks pretty like a smooth, homogeneous field as far as we can tell. I mean, to really see it, probably we'd have to be looking out at scales that would be like, I don't know, not even just beyond our solar system, but beyond the distance to typical stars in the Milky Way. We're talking about scales of, of thousands of light years or more than that before you'd start to really see the effects of dark matter. And part of that is that the mass of normal matter around us is just so much higher. The density of atomic matter is so much higher. The dark matter just is lost in the background. It's only on the biggest scales that you start to see the dark matter and then the dark energy more and more.
How can we say that there's like 5 times more dark matter than normal matter if there's so much more normal matter around us?
Yeah, it's a great question. So I think there are a few places, we can see if you look at these galaxies and look at how fast objects are spinning around them. You can sort of ask that as a function of distance out from the galaxy. And so from sort of close in like we are, maybe you see more regular matter, but the further you go out, the more dark matter you see. You can see that get to some sort of constant value maybe. The other thing is if you look at the microwave background radiation, you can ask how are the very detailed properties of those maps of the microwave background radiation, because we can take a picture of the full sky and see these fluctuations from point to point. And that would tell us how much regular matter there is versus dark matter. And that's 5 to 1 again. So the number from the galaxies is the same as the number there. And then if we go back to that Big Bang nucleosynthesis and we ask how much atomic matter can there be to form the helium that we see, and then how much more matter must there be beyond that, that's again 5 to 1. So again, this is sort of one of the reasons we feel very confident in dark matter as we look on very different scales and at very different times in the universe, and we get a very consistent picture about the abundance of the dark matter relative to atomic matter, and it's the necessity of dark matter in all those eras.
Can we observe any gravitational lensing of light from dark matter?
Absolutely. So, so gravitational lensing is when light, takes light's path gets bent by the mass. So mass is basically acting as a lens, and so sometimes that can even mean that if you have the right configuration, light can take 2 paths and get bent back towards us, so we can see the same thing twice in 2 different directions on the sky.
Oh, that's really cool. Yeah.
So that's multiple imaging, dark lensing or strong lensing. But yes, some of the lensing models that we have, if you don't account for dark matter, you get things totally wrong. So you can see there's a cluster of galaxies. You mostly just see individual galaxies, but the mass that's there, that has to be there to cause the light to bend like you see it, that requires a lot more mass than would be there just by adding up the mass of all the galaxies. So there's something else, the dark matter there. And that's helping us boost the things we can see with the James Webb Space Telescope. So we see these clusters of stars around us that are all basically the age of the universe almost. They're 13.7, 13.6 billion years old, we think. And they're maybe a few light years in size, okay? We can see those same things now with James Webb on the other side of the universe because of this gravitational lensing. So in very rare configurations, that means we can see much better because it's like a cosmic magnifying glass. We can see much better. So it's only for tiny portions, but we can see at 25 billion light years away these things that are 4 light years in size. Amazing, right? It's crazy.
How can we observe galaxies that are 25 billion light years away when our universe is only 12 to 14 billion years old?
Right. So let's say the universe is 14 billion years old roughly. So you might think, okay, that means that light can have traveled 14 billion light years, because a light year is how far light can travel in a year. And if the universe wasn't expanding, that would be true. But it's really that expansion that does it, because as the light is traveling, the universe is expanding, and so light gets to go that extra distance through the expansion. It's sort of like if you're walking at 2.5, 3 miles an hour, let's say, in an airport, and I'm walking next to you and I'm lazy and I say I'm going to take the people mover, or not lazy, just want to take the people mover, and you're like, I'm trying to get some exercise, I'm just going to walk, even if we're walking at the same speed, I'm going to get farther than you if I'm on the people mover, because the people mover is dragging me along with it, right? So it's the same for the universe, that even if the light is going at the speed of light, it can go farther because the universe is expanding.
I always thought that it would go slower, like there would be more and more distance to cover, so that light would just. I mean, light would travel faster than the expansion of the universe, but it would slow down everything.
I can see what you're saying, but it does mean that it gets to travel bigger distances than
Yeah, it's a fault in my understanding. Yeah,
but the universe is getting so much bigger that that it still means there's more universe that it can't cover. But it does, you can sort of think of it again. It's an imperfect analogy, but it's like the surface of the balloon, right? And as you sort of as you're going along it, as the balloon is expanding, it's getting to go further than it would have if it was just traveling along that balloon that was one fixed size. But of course, the balloon is much bigger, so it doesn't look like it's made much progress.
That's really cool to think about. Breaks my idea of what I thought was true.
Yeah, there's a lot that it takes some readjusting the mental picture to get into it for understanding the universe on the biggest and the smallest scales.
So we can observe, just based on like how big the universe was in its inception and then subsequent formation of stars and everything. So we can observe that. So theoretically, we could observe the beginning of almost everything in the universe had we like an infinitely powerful telescope.
Well, yes and no. So I think the microwave background gives us this limit as to where regular light can go, because basically before that, everything was bouncing around so much, there's nothing to see through, right? You can't get past that. But gravitational waves might be able to get through that. And so we might, if we have the best gravitational wave telescopes, maybe we can see these earliest phases. And so people are looking, including people at UT, are looking to use gravitational waves to probe way, way earlier, the first fraction of a microsecond of the universe. And that would be super amazing, that you could really see signatures of things that happened well before even those first atoms started to fuse, right? It's not really seeing it the same way like with your eyes, but you'd see the statistical signatures of that in the distribution of gravitational waves, which is pretty amazing.
Yeah. You're talking to the perfect person, because all of geophysics is making observations with seismic waves or electromagnetic stuff you can't see with your radio waves. When I say electromagnetic stuff you can't see with your eyes. I talked to Shoemaker a couple episodes ago. She does a little bit of that.
Oh, she's big into gravitational waves.
But I didn't get to talk to her about the timeline of the universe. I think she had to leave. But
that's too bad.
Yeah, we did talk about the collision of neutron stars and black holes and all that stuff.
Yeah,
it's so cool. And I remember during one of your talks, you were talking about how most of the elements that we can observe were created in these collisions and other kind of supernovae. But there was a question where they were asking, like, well, what about just a normal star exploding? Like, why does it have to be colliding neutron stars? And I think you had said at the time that there was research that was saying that you need to have the conditions of colliding neutron stars, or I think it was colliding neutron stars, to create a lot of the heavier elements that we see, and you can't create that with like a exploding, massive sun or something.
That's right. So some of the, you can, the way you get heavier and heavier elements, starting with the lightest ones, often is you're just burning together, bringing together two lighter elements, fusing them to form a heavier one. And that's a process that releases energy, so it's energetically favorable to kind of do that. And that's the way fusion bombs work or something like that. You're just bringing things together and out comes light and heavier stuff. But once you get to iron, you can't get any more energy by fusing heavier and heavier stuff. So you actually have to put energy in to do it. And you can do that for some things with supernovae, but the other way you can get heavier elements is not to have these sort of regular stuff around, you need neutrons, and free neutrons just aren't out there normally. But a neutron star is just a big ball of neutrons. And so having those neutrons available changes the kind of energy calculation. So if you have this neutron-rich environment, that can really change and get you up to these heavier, gold, platinum, things like that. That can help you get to these heavier elements much more easily than it would be in even an exploding star, which you think of as an energetic environment. But it's still hard for stuff to meet up as the thing is exploding out. So you really need this neutron-rich environment to do it, we think.
And the star composition of these fringe galaxies that you're talking, these like fossilized galaxies, is it white dwarfs? Is it neutron stars?
Great. Yeah, so basically what we think is they form the same kind of stars that form in the Milky Way, anything from about 1/10 the mass of the sun to maybe 100 times the mass of the sun. Okay, but as time goes on, those heavier and the heaviest ones die first, and then lighter and lighter and lighter. So what we see is there's nothing heavier than about 70% the mass of the sun in those galaxies. So we only see the low mass stars and the remnants. So there'd be white dwarfs, there'd be neutron stars, there'd be black holes, and there'd be stars that are less massive than about 70% the mass of the sun. But there's nothing that's more massive as a star that's shining than 70% the mass of the sun. And that's how we know that it's one of these fossils, because all of those stars have died. There are no more of those anymore. And that's because it's been around so long that they've burned out all their fuel.
Something that I mean, you would definitely be able to tell me more about this, but an idea that I think about whenever I think about these fringe galaxies is that over time you're going to go through the natural evolution or life cycle of stars, and so you're going to end up with like neutron stars and white dwarfs, and then black holes, and black holes do merge with each other. So maybe as you're just forming smaller black holes, there's enough. I mean, they're probably too far apart to ever interact with each other. But
yeah, that's a great point. I think that it's rare that they merge, and they do sometimes. But yeah, normally one's forming over here, one's forming over here, and there's so much space in between that it's really hard to get down to each other.
Yeah. What about when two galaxies are crashing into each other, for lack of a better term? I'll ask about the black holes first.
Yeah.
So those black holes will probably find each other. Say you have Andromeda and the Milky Way. Those black holes will probably find each other and create an even bigger black hole.
The one at the center probably will find each other, yeah. And that's because the central mass will sort of attract each other especially, and eventually it'll sort of smush together, yeah.
What does the dark matter look like in that merging of two galaxies?
Yeah, for a while it'll kind of be this random kind of chaotic stuff, but eventually it will settle down to be again kind of a bigger ball around the Milkdromeda or whatever, the combined Milky Way Andromeda system.
Would it look like it probably wouldn't look like two planets colliding, but would it look like two kind of like gaseous balls that you could stick your hand through, just kind of slowly merging together? Or would there be more collision?
Yeah, so what you'd probably see is there'd be two lumps, and they'd kind of pass through each other, but then kind of come... Excuse me.
No, you're good.
They'd be two balls, and they'd kind of pass through each other, and then they'd come back and go back, and they'd slowly kind of oscillate down and then sort of overlap and come to a final configuration.
Does that oscillation create gravity waves?
So it would probably create some very low frequency gravity wave, but nothing that would carry a lot of energy. But definitely that is, people look for gravitational wave signatures of merging black holes, especially, not merging galaxies themselves, but the black holes. That's one thing we can look for.
Yeah, that's really cool. Like you get this kind of this ring down of these dark matter bodies. I mean, it's amazing that you guys can simulate this. Like you can't. There's no way you could ever observe this.
Yeah, as far as we know,
with what we have right now.
With what we have now, yeah. And so it's pretty cool. It's pretty amazing.
Yeah. And as far as so if there was a fringe galaxy that was merging with the Milky Way or Andromeda or something, would it just kind of like slowly be eaten, and it would, like, if you were, let's say humanity's still around by that point, the likelihood of that is a separate conversation, but let's say that we're still around, would we feel any of the effects of that besides just a different looking night sky? Or
I don't. So the merger of Milky Way and Andromeda, probably we wouldn't even feel anything there. It'd be a very different night sky for sure. But our gravity is dominated by the nearest stars, and so unless something happens to perturb the sun and things like and the orbit there, nothing we'd expect to happen. I mean, unless something shakes something loose in the asteroid belt, like you're saying. But the space between stars is really big, right? Our nearest star is 4 light years away or something like that. And so something's got to come that close. It's very unlikely that even when we merge 2 big galaxies together, that'll happen. But if you look at the galaxies themselves as they fall in, they do get shredded. They turn into sort of big tails of stars. Get spewed off. So it looks really cool on the big scales, but on the scales that we live, nothing.
you wouldn't feel a thing.
Of course, the sun would have burned out by then,
Yeah,
so you might feel something different. But if you were just a sentient body out there.
Yeah, we wouldn't feel anything in our AI hive mind.
That's right, in the Matrix.
Robot planet, yeah, right next to our Dyson sphere. What about the Hadron Collider? How is that? I mean, how are they using that to study dark matter?
Yeah, I think that's a great question. So basically, the Large Hadron Collider is one of these few places where you can recreate the energetic conditions that would be comparable to the very early universe. So it's smashing objects together, subatomic objects, but still objects with enough energy that they can create conditions that have not existed in the typical part of the universe for billions of years. And so by studying that, we can really study what the early universe looked like. So that's one way. Another way is that the properties of some of the particles, if we can see them, would tell us about properties of dark matter potentially. So it's possible you could create dark matter at these colliders. That's one of the things that people look for. And so that would be really exciting if we could see dark matter or something that'd be related to dark matter at these colliders. So there is a lot of synergy between the two fields.
And how successful has that been in actually?
So I think recently it hasn't been so successful. And I think it hasn't been successful in discovery space, I'd say. So it's been successful in eliminating possibilities, but that's a little less exciting because there's so many possibilities out there. But for a long time, it was very successful in the sense that it helped us understand all of the constituents of the universe, and those are the inputs we need for our models to make the universe. So that was a great kind of coming together in the 70s of particle physics and astrophysics to understand, those conditions of the early universe and properties of dark matter, things like that. So overall, it's been very successful. Recently, it's been hard because nothing's kind of come out that's been new from the particle physics side of things. It's more been eliminating possibilities. But, Sherlock Holmes said, eliminate the impossible, or, and whatever is left, however improbable, has got to be the truth, or something like that. I'm sure he said it much more eloquently.
There's the detective archaeology
influence
coming out.
A lot of archaeology detective kind of analogies.
Love it. So how is that collider working exactly? Are they like accelerating a proton in this ring just like over and over and over again?
Yeah, that's right. So it's LHC stands for Large Hadron Collider. So a hadron are composite sort of heavy particles, so things bound by the strong nuclear force. So this is a proton collider. So it's smashing together protons, and that's good in the sense that protons are heavy, and so you get them going fast enough, and they smash. They have a lot of energy, but they're also made of dense nuclear material. So there's a lot of junk, sort of in some ways, technically speaking, that comes out with that. So the one of the biggest ones was the Stanford Linear Accelerator, and that is one that was colliding electrons and anti-electrons, and so that was very good in the sense that there wasn't all this nuclear junk coming out. It was just basically pure particles. And so, there's some thoughts for future colliders that maybe you could take not electrons, but muons, which are basically like very heavy electrons. They're 207 times the mass of an electron. And so if you could collide muons and anti-muons, you'd have all the benefits of smashing together protons in some sense, but also all the benefits of smashing together electrons. So that's one hope, but the technology is, we're talking 30, 40 years off for anything like that. And the James Webb Space Telescope is a $10 billion machine. The Large Hadron Collider is even more expensive. And then, creating the next one, they're talking about a $50 billion kind of machine. So this is, we're talking about GDP of a small country kind of thing. So it's really as big science. And these, you have to ask, we don't have many chances. We can't build lots of these. Maybe we can't even build one. How should we do it if we build one? And these are the things that people are vigorously debating these days, and how do you fund it? Elon Musk or whatever.
Yeah, I was about to say, like, how much of that is public funding, and then also how much of that is private?
It's basically 100% public funding. There's no level of private funding for that kind of work. Now, at the level of $100 million, you could probably do something where there's a lot of private funding, but these biggest ones are all government sponsored.
Yeah. And it's like an international, EU, America, China, like everyone working together. Yeah.
Yeah, I mean, it may not be everyone, but definitely international collaboration, and there have to be international agreements and treaty. I mean, you really have governments are involved, right? It's very high level stuff.
And yeah, so it's like just this massive, like, how big of a radius does it have?
I don't remember now exactly. I think it's 26 kilometers, maybe the ring. And I don't remember whether that's the diameter or circumference. But these are huge rings that they're really needing to make. And there's been enormous progress in that over 100 years. I mean, you see some of the first particle colliders they could probably fit on a tabletop, right? And now we're talking about many kilometers in radius. It's wild.
So more circumference equals more energy, like more speed.
That's right.
Higher power collision.
So you run things around longer and longer, and it's got a bigger path length that it can go to smash together. And the sort of, you don't have to, if it's really tight, it has to bend around, and so the energy losses can be large sometimes. There are a lot of considerations anyway.
Yeah, or an interesting point in my conversation with Shoemaker was that you can create like microscopic black holes when you collide those particles, and super unlikely. But yeah, we were like, what would that look like if we were just like having a normal day, and then all of a sudden everything just goes black and all sucked into a black hole?
I guess we wouldn't know. Yeah. But, it hasn't happened yet, as far as we know. Yeah, so all good. No, but I think the other thing is these kind of collisions happen all the time in nature. All the time, way more often than we can make it happen. So we feel pretty good that it shouldn't be something that we're going to have to worry about. So I think don't hate your local particle physicists. They're all doing the Lord's work or whatever, so to speak.
Speaking of collisions that we're detecting, can you walk me through the xenon detectors?
Okay, yeah, sure. So these are for detecting dark matter particles. So one of the, dark matter we think doesn't really interact except with other dark matter, but that's not quite true. Very once in a while, a dark matter particle might smack off of a regular nucleus and send it shooting off in a different direction. So it'd be very rare. So you have to collect up a lot of the stuff. And you also don't want it to be that it's just some other random particle that happened. And so you want to shield this very well. So what you want is something that's very inert, so there's not lots of random junk happening internally. You want it shielded, so it can't be lots of stuff happening externally, and you want a huge amount of it. So what this boils down to is the inert is something like a liquid noble gas. So noble gases on the periodic table are very inert. So xenon is one that people use a lot. It's heavy and inert. And so you build a detector that is basically as much xenon as you can find. And we're really talking about like taking a lot of the Earth's supply of xenon that people have found and filtering it by a factor of 1,000,000 in purity to get out the isotopes that aren't what you're looking for. And then putting it a mile underground, so in like old mine shafts, so there's no cosmic rays streaming down and doing things, and then just sitting there and waiting to see something. So these are what people are building. They're literally 1 ton, bigger than 1 ton now of liquid xenon. It's just sitting there underground waiting for hopefully a dark matter particle to smack it, hit a nucleus, and that nucleus to give some signature in the detector. And they're so sensitive now that people are starting to detect neutrinos through this instead of detecting dark matter, because neutrinos can go through that mile of Earth just like dark matter can. So pretty amazing.
That is really cool.
So they're now starting to be neutrino detectors.
Yeah. And then there's a whole like neutrino observatory in the Antarctic, which is pretty cool.
Yeah. Looking underground, buried in the ice, ice cube. Yeah.
Is it called Ice Cube?
Yeah.
That's cool. That's a good name. So my area of geophysics that I've done a bit of undergrad research is the polar geophysics.
Mm-hmm.
So there's a lot of people going to Antarctica to do geophysical work there, and they talk about the physicists at South Pole a lot. And how it's like this new crowd that's all going over there.
Yeah. No. So there are a lot of people doing physics experiments there, astrophysics. So it's a desert. People don't think of it like that, right? But it's a desert, and so there's very little water vapor in the atmosphere. So it's great for telescopes, but again, kind of a remote location, and takes an act of Congress to get things going there. So you got to be pretty careful. But it's an amazing resource. I hope you get to go someday. That would be amazing.
That would be cool too. Yeah, I hope so too. We'll see. It's really high elevation too.
Yes.
I think a lot of people don't consider that. They're like, oh, it's ice. It's probably like
sea
it's
level.
next to the ocean. Yeah, but it's really high up. Like, when you're up in the mountains, you're maybe actually don't know what the elevation of the mountains are, where South Pole is, but the ice itself is like, anywhere from 2 to 4 kilometers thick. Like it's, yeah, and it's all stacked up on top of already existing somewhat high topography. Antarctica's got pretty low topography.
Right.
Yeah.
Well, let's hope we can keep it as ice and not turning into water.
As stable as possible. Yeah.
Definitely.
Yeah. I think that's I ran through every single question
Awesome.
I could think of. Yeah.
Well, no, I appreciate it. I should probably get running anyway because I got a couple other things to do. But I'm very impressed with all your questions. You definitely.
Oh, thank you.
I don't know how you hold it all in your head, and you got notes, but still, like you, very knowledgeable. It's very cool. So, and this is fun to talk about.
Thank you. I appreciate it. It's just a lot of practice. A lot of practice.
Well, but it takes a lot to be able to speak knowledgeably about a lot of different things. So I'm definitely very impressive.
Oh, the same goes to you. Yeah. I think you're a really great speaker. Like, you're good. I watched some of the, I forget exactly what it's called, like Astro on Tap or.
Oh, okay. Yeah.
Astronomy on Tap.
Yeah.
Those talks are really good.
Okay.
Like,
cool.
Yeah,
Thanks.
and I think my opinion might be more valuable than some other people because I sit through so many talks to do research for this podcast.
Absolutely, yeah.
And I've listened to a lot of scientists give talks and stuff, and you seem very calm and you're cracking jokes, and everyone's like, really engaged in it. And
well, thanks. I appreciate that. It means a lot. Yeah, like you say, especially coming from somebody who digests a lot, for sure.
Yeah. Cool. Well, thank you. I wish you the best of your research. And
thanks very much.
Best of luck with the rest of your day.
Well, and best of luck with your research. I'm sure you're going to go far no matter what you end up.
I appreciate it. Thank you.
Cool. All right. Thanks
Yeah.
a lot, man.
Yeah. Thank you.
I'll be excited to see you.